The universe starts to feel less like a machine and more like a story, shaped by chance within boundaries, a kind of structured randomness. And that idea is going to come back later in a much bigger way, because what we're seeing with planets is just a small scale version of something much larger. Zoom out past Earth, past the other planets, out to the entire solar system. What you see is not random. Planets orbiting in roughly the same plane, most moving in the same direction. Distances that aren't perfectly regular, but not chaotic either. It has a kind of quiet order to it. And for a long time, we thought this was just how solar systems work. Neat, stable, almost polite. Then we started looking at other stars, and everything got weird. We found planets on tilted orbits, planets moving backwards, giant planets where small ones should be, systems that look like they've been rearranged violently, which means our solar system might not be the rule. It might be the exception. And that raises a question that's a little unsettling. If even solar systems don't follow a single pattern, what happens when we zoom out even further? Because stars themselves, these massive glowing engines, don't form in isolation. They're part of something bigger, something with its own structure, its own rules, and its own kind of hidden order. And once you see that structure, the scale of this whole story is going to jump again in a way that makes planets feel almost small. A star is not born quietly. It begins as a whisper, just a slightly denser region inside a vast, cold cloud of gas and dust. Nothing dramatic, nothing you'd notice if you were somehow floating nearby. But density is destiny. That slightly heavier patch pulls in more material, slowly at first, then faster. Gravity doing what it always does, turning small imbalances into irreversible outcomes. And as the cloud collapses, something strange happens. It starts to spin, not because anything pushed it, but because of conservation of angular momentum. A fancy way of saying that as things pull inward, any tiny rotation gets amplified, like an ice skater pulling in their arms and spinning faster. Except now, the skater is a cloud larger than our entire solar system. The collapse doesn't form a sphere right away. It flattens into a disk, a swirling, glowing pancake of gas and dust with a growing knot of heat and pressure at the center. That center is where the star will be born. But not yet. Not until the pressure becomes so intense that atoms start to fuse. Fusion is one of those words people hear a lot, but rarely sit with. So let's slow it down. Imagine trying to push two magnets together, north to north. They resist, strongly. Atomic nuclei do the same thing. They're both positively charged, so they repel each other. To force them together, you need absurd pressure and temperature, the kind you only get when you have a massive cloud collapsing under its own gravity. And when they finally overcome that repulsion, when they touch, they snap together and release energy. A lot of it. Light, heat, radiation. A star turns on. And just like that, you go from darkness to something that can outshine entire planets. But here's the part people don't always realize. A star is not on in the way a light bulb is. It's balanced. Barely. Gravity is pulling inward, trying to collapse it further. Fusion is pushing outward, releasing energy and pressure. And the star exists in that tension, a constant negotiation between collapse and explosion. If gravity wins, the star shrinks. If fusion wins, it expands. Most of the time, they reach a truce, and that truce can last billions of years. I remember the first time I really understood that the sun isn't just there, it's constantly fighting itself, every second, for billions of years, and somehow maintaining this delicate balance that allows life to exist on a small rock orbiting at just the right distance. It feels stable from here, but it's anything but. Now go back to that disk around the forming star, because while the star is igniting, the leftovers are still there. Gas, dust, fragments, and they haven't stopped interacting. They're colliding, sticking, breaking apart, reforming. Sound familiar? It should. This is where planets come from. Again, same process, different scale, structure building on structure. But here's where it gets interesting. The star dominates the system. Its gravity sets the stage. Its radiation heats the inner regions, blows away lighter gases, shapes what materials can exist where. Close to the star, it's too hot for volatile compounds like water to stay intact. So you get rocky planets. Farther out, it's cooler. Ices can survive, gas can accumulate. You get giants, Jupiter, Saturn, massive worlds that never became stars, but got close enough to blur the line. And those giants, they're not just passive residents, they shape everything. Jupiter, for example, acts like a gravitational bouncer, deflecting comets, capturing debris, sometimes sending objects inward toward the inner planets. It protects, and it threatens. Same force, different outcomes. This is a pattern you'll start to notice. In the universe, the same mechanism can create and destroy depending on context. Gravity builds stars and collapses them into black holes. Radiation enables life and strips atmospheres. There are no purely good forces, just forces. And solar systems, as it turns out, are not static. They evolve. Planets migrate. Orbits shift, sometimes dramatically. We've seen evidence that Jupiter itself may have moved inward early in our solar system's history, then reversed course, a cosmic detour. And if that's true, it would have reshaped everything, scattering material, influencing the formation of Earth, possibly even affecting whether life could emerge here. A small change in position, a completely different outcome, which brings us back to that idea. The rules constrain. They don't dictate. You can have the same ingredients, gravity, gas, dust, and end up with wildly different architectures. Some systems are tightly packed, with planets orbiting closer to their star than Mercury does to the Sun. Others are sparse. Some are stable. Others look like they're one bad interaction away from chaos. And then there's something even stranger. Most of the stars you see in the night sky aren't alone. They're part of binary or even triple systems, 2 or 3 stars orbiting each other in complex gravitational dances. Imagine having 2 suns in your sky, sunsets that never quite get dark, or gravity pulling in competing directions, making stable planetary orbits much harder to maintain. And yet, planets exist in these systems too, structure finding a way, even in complicated environments. So now, step back. What do we have? A star, a system of planets, asteroids, comets, debris, all orbiting, interacting, evolving. It feels complete, like a self-contained unit. And for a long time, that's how we thought about it. Solar systems as isolated islands. But that's not what they are, not even close. Because stars themselves are not randomly scattered. They cluster, they form groups, families, entire cities of stars bound together by gravity. And these cities have structure, shape, history. They collide, merge, stretch, distort. They're not static backgrounds in the sky. They're dynamic, living systems on scales that are hard to even picture. And here's the shift. Everything we've talked about so far, atoms, planets, solar systems, they're not the main level of organization in the universe. They're substructures, pieces of something much larger. And once you see that larger structure, you start to realize that even stars, the things we've been treating as central, are just tiny points in a much bigger pattern. A pattern that at first glance looks almost impossible, like the universe zoomed out and started thinking in terms of entire galaxies. And that's where things stop feeling familiar and start feeling enormous. If you could leave the solar system, really leave it, not just drift past Pluto, but keep going far beyond the distant cloud of icy debris that still feels the sun's pull, you'd eventually reach a kind of darkness that feels different. Not empty, just less crowded. The sun would shrink into just another star, one point among thousands, then millions. And somewhere in that slow transition, something subtle would click. You're no longer inside a system, you're inside a city. We call it the Milky Way, which sounds soft, almost poetic. But it's not soft. It's a gravitational machine, holding together somewhere between 100 and 400 billion stars. That's not a typo. Billions, each one potentially with its own planets, its own debris, its own little story of structure building on structure. And all of them, every single one, are moving, but not randomly. This is where the idea of structure comes back in a way that's almost unsettling, because galaxies are not just blobs of stars. They have shape, spirals, bars, halos, patterns that persist over immense spans of time. And the question is, why? I remember the first time I saw a high-resolution image of a spiral galaxy, not a cartoon, not an artist's impression, a real one. And it didn't look like what I expected. It looked deliberate, arms curving outward in perfect logarithmic spirals, like something you'd see in a nautilus shell or a hurricane viewed from space. The same geometry repeated across scales that have no business being related. And yet, there it was. A pattern that felt almost too clean for something born out of chaos. But those spiral arms, they're not what they seem. They're not fixed structures like the arms of a pinwheel. They're more like traffic jams, regions of higher density moving through the galaxy. Stars enter them, slow down slightly, cluster, then leave. The arm persists even though the stars within it change. It's a pattern made of motion, a structure that exists without being made of the same pieces. Think about that for a second. It's like a wave in a stadium. The wave moves, but the people don't travel with it. Structure without permanence. And this is where galaxies start to feel less like objects and more like processes, ongoing, evolving, never quite finished. At the center of most galaxies, including ours, there's something even stranger. A black hole. Not just any black hole, a supermassive one, millions or even billions of times the mass of the sun. And it sits there, quietly, at the core, not sucking everything in like some cosmic vacuum cleaner. That's a common myth, but influencing the entire structure around it. Here's an obscure detail that doesn't get talked about much. We're not actually sure how these supermassive black holes got so big so early. Some of them formed when the universe was still very young, too young according to our simplest models to have grown them through normal processes, which means either they formed through mechanisms we don't fully understand, or our understanding of early structure formation is incomplete. And that's not a small gap. That's a crack in the foundation. But even without solving that mystery, we can see their effects. Stars orbiting the galactic center at incredible speeds, jets of energy blasting out from active galaxies, stretching thousands of light years into space. Entire regions shaped by something we can't directly see. Again, structure emerging from invisible influences. And then there's the halo, a vast spherical region surrounding the visible galaxy. It doesn't glow like the spiral arms. You can't see it directly. But it's there. We know it's there because of how stars move. They orbit faster than they should if only visible matter were present. Something else is adding mass. Something we can't see. Dark matter. Now, dark matter sounds like a placeholder name. And in a way, it is. It just means we don't know what this is, but it has gravity. It doesn't emit light. It doesn't absorb light in any obvious way. But it shapes galaxies. It acts like a hidden scaffold, a structure behind the structure. Without dark matter, galaxies as we know them might not exist. They wouldn't have enough gravitational glue to hold together. They might never have formed those elegant spirals. They might have just dispersed. So now the picture gets stranger, because the visible galaxy, the stars, the gas, the dust, that's only part of the story. Maybe a small part. The real mass, the real structure, might be dominated by something we can't directly observe. And this flips our intuition. We tend to think of what we see as the main thing. But on cosmic scales, visibility is not importance. Light is just a thin layer on top of a deeper, darker framework. And galaxies don't just exist alone. Just like stars cluster into galaxies, galaxies cluster into something bigger. Groups, clusters, collections of dozens, hundreds, sometimes thousands of galaxies bound together by gravity, interacting, merging, stretching each other into distorted shapes. I once saw an image of two galaxies colliding, not crashing like cars, but passing through each other slowly over millions of years. Their shapes pulled into long tidal tails, stars flung out into space like sparks from a fire. And here's the weird part. Individual stars almost never collide. There's just too much space between them. So the collision is really about structure interacting with structure, fields overlapping, gravity reshaping everything. And from these interactions, new structures emerge. Elliptical galaxies, larger systems, more complex dynamics. It's like cities merging into megacities. So now zoom out again. We've gone from atoms to planets to stars to galaxies to clusters of galaxies. And at each level, the same themes repeat. Gravity pulling things together, initial conditions shaping outcomes, structure emerging from simple rules. But here's where it breaks, or at least where it stops being intuitive. Because when you zoom out far enough, the universe doesn't look like a random scattering of clusters. It looks like something else entirely. Something with filaments, voids, connections stretching across hundreds of millions of light years. A pattern so large that calling it a structure almost feels inadequate. And once you see it, you can't unsee it. Because it doesn't just look like a network, it looks familiar in a way that's hard to explain, like the universe accidentally mirrored something much closer to home. And that resemblance? It's going to raise a question that's a little uncomfortable. Because the largest structure we know might not just be big. It might be telling us something about how the universe builds everything. And maybe, even more strangely, about how we build understanding itself. There's a moment, usually around the first time you see it, where your brain just hesitates, not because it's complicated, but because it's too familiar. It's a map of the universe, not stars, not galaxies as little dots, but something deeper. A reconstruction of where matter actually is on the largest scales we can observe. And it doesn't look random. It doesn't look like scattered grains of sand. It looks like a web, filaments stretching across unimaginable distances, nodes where those filaments intersect, bright, dense clusters of galaxies. And in between, voids, vast regions with almost nothing in them. Not empty exactly, but close enough that, on this scale, they might as well be. It looks like a sponge, or foam, or, depending on your mood, something eerily biological, like neurons, like the branching patterns of a brain. And yeah, that comparison gets thrown around a lot, sometimes too casually, because the universe is not a brain, and your brain is not a universe, but the resemblance is just strong enough to make you pause. I remember the first time I saw a side-by-side image. On one side, a simulation of the cosmic web. On the other, a slice of neural tissue. And for a split second, I couldn't tell which was which. That's not because they're the same thing. It's because similar rules can produce similar patterns. This is the part where structure stops feeling like a series of isolated levels and starts feeling unified. So how does this web form? We go all the way back to when the universe was young, not stars and galaxies young. We're talking plasma, a hot, dense soup of particles so energetic that atoms couldn't even exist yet. Just protons, electrons, photons, constantly interacting, scattering, exchanging energy. It was almost uniform. Almost, but not perfectly. There were tiny fluctuations, regions that were just a little denser than others. We're talking differences of 1 part in 100,000, so small they feel irrelevant, like a barely noticeable ripple on a perfectly still lake. But remember what we said earlier. Small differences don't stay small. As the universe expanded and cooled, those tiny overdensities became seeds. Gravity started amplifying them, pulling in more matter, making dense regions denser and empty regions emptier. A feedback loop. Again, dark matter played a huge role here. Before normal matter could clump effectively, dark matter, interacting mostly through gravity, started forming the first scaffolding, invisible structures, frameworks, and then ordinary matter fell into those gravitational wells. Gas accumulated, stars ignited, galaxies formed along these filaments. So the cosmic web isn't just a pattern, it's a history, a fossil record of how structure grew from almost nothing. And here's an obscure detail that's kind of wild. We can still see echoes of those original fluctuations in the cosmic microwave background. A faint glow left over from when the universe first became transparent. If you map its temperature variations, you see tiny differences, hotter and cooler spots. Those spots correspond statistically to where structure would later form. It's like looking at baby pictures of the universe and recognizing the adult face. So the largest structure we know comes from the smallest imperfections imaginable. Now pause on that, because it flips something in your intuition. We tend to think complexity requires complexity at the start. But here, simple beginning, tiny variations, and then time, gravity, and expansion doing the rest. And the result is this vast network. Galaxies tracing out filaments like cities along highways, clusters acting as intersections, voids stretching between them like cosmic deserts. And we live inside one of those filaments, inside a galaxy, inside a solar system, inside a planet, inside a structure, within a structure, within a structure, nested all the way down. But here's where it gets uncomfortable again, because the cosmic web might not be the final level. It's the largest structure we've observed. That's an important distinction. Observed, limited by how far light has had time to reach us, limited by the expansion of the universe, limited by the fact that beyond a certain distance, things are receding faster than light can ever bring their information to us. So when we say the observable universe, what we really mean is the part of the universe we're allowed to see, not necessarily the whole thing. And that raises a question that doesn't have a clean answer. What lies beyond? More of the same? More filaments? More voids? Does the pattern repeat? Does it change? Does it even make sense to ask? Because there's a possibility, just a possibility, that on scales far larger than what we can observe, there are structures we can't even conceptualize yet. Not because they're complicated, but because our brains evolved to deal with things on the scale of meters, maybe kilometers, not billions of light years. It's like trying to explain an ocean to a fish that has only ever known a puddle. The concepts start to stretch, then break. And this is where science starts to blur into something more philosophical. Because structure isn't just out there, it's also in how we perceive, how we model, how we make sense of patterns. We look at the cosmic web and see familiarity, networks, connections, nodes, but that might say as much about us as it does about the universe. Still, the pattern is real. The filaments exist. The voids exist. Gravity shaped them. Time evolved them. And we are inside it, not observers from the outside, participants, tiny pieces of a structure so large that even describing it feels like approximation. And here's the thing that lingers. If the universe builds structure this way, from tiny fluctuations through simple rules into nested, repeating patterns across scales, then the obvious question is, does it stop? Or are we just somewhere in the middle of a much larger hierarchy? Because we've already seen this pattern before. Atoms forming molecules, molecules forming materials, materials forming planets, planets forming systems, systems forming galaxies, galaxies forming webs. Each level feels complete until you zoom out. So what happens if we zoom out again? Not with better telescopes, not with more data, but with imagination guided by physics. Are we inside something larger? Something where our entire cosmic web is just a small component? It sounds speculative, and it is, but not baseless, because the same logic that led us from atoms to galaxies is quietly pointing forward, suggesting that the story of structure might not be finished yet. And if that's true, then the most unsettling possibility isn't that the universe is big. It's that what we call the universe might itself be just one layer of something, even deeper. And in the final part of this journey, we're going to step right up to that edge where science runs out of clear answers. And we're left with the patterns, the rules, and a question that refuses to go away. Is structure the end point? The solar system is not a collection. It is a process. 8 planets do not simply sit in their orbits like marbles in a box. They hold each other in place. They tug. They influence. They trade momentum across the void in ways that are invisible but absolute. Remove Jupiter, and the asteroid belt does not stay where it is. Remove Saturn, and Jupiter's orbit shifts. The entire configuration is contingent. each planet is where it is because of where every other planet is. This is what it means for something to be a system. The solar system begins with the sun. Not because the sun created the other planets, though gravity pulled the dust together that became them, but because the sun is massive enough that its gravity dominates the conversation. The sun contains 99.86% of the solar system's total mass. Everything else, 8 planets, dozens of moons, thousands of asteroids, billions of comets, orbits in the gravity well the sun creates. Alone, the sun's gravity would hold all of these objects forever. A planet in a stable orbit around a single star is a simple problem. Newton solved it. The math is clean, but the sun is not alone. Jupiter is the second most massive object in the solar system. It is small compared to the sun, about 1,000th of the sun's mass, but it is massive enough that its gravity matters. Its gravity is strong enough to bend the orbits of other planets. Its gravity is strong enough to eject asteroids from the asteroid belt. Its gravity is strong enough to have shaped the entire configuration of the inner solar system. Saturn, Uranus, and Neptune have their own gravitational influence, though less than Jupiter's. In the earliest moments of the solar system, in the first million years after the planets formed, the configuration was different from what we see today. Planets migrated. They moved inward and outward as they scattered asteroids and traded gravitational momentum. The NICE model, developed in the 2000s, proposed that Jupiter and Saturn were once closer to the Sun than they are now, and that they migrated outward in a process that destabilized the inner solar system and ejected most of the asteroid belt into the outer reaches. This is not ancient history. This is a fundamental property of how the solar system works. The system is in dialogue with itself. Each planet's orbit is not fixed. It oscillates slightly over thousands of years. These oscillations are caused by the gravitational tugging of the other planets. Saturn pulls on Jupiter. Jupiter pulls back. The inner planets feel the influence of the outer planets across the void. These oscillations are small. Jupiter's orbit does not shift by more than a few percent, but they are real. They are measurable. They are proof that the solar system is not a static structure, but a dynamic process, with each component constantly negotiating its position with every other component. But why do the planets stay in their orbits? Why does Jupiter not spiral into the Sun? Why does Mercury not fly off into interstellar space? The answer is resonance. When two objects orbit the same center of gravity and their orbital periods are related by a simple ratio, they enter a resonance. The most famous example is the Laplace resonance between Jupiter's 3 largest moons, Io, Europa, and Ganymede. For every 4 times Io orbits Jupiter, Europa orbits twice, and Ganymede orbits once. This 4-2-1 resonance has locked the 3 moons into a stable configuration for billions of years. The planets do not have such clean resonances with each other. Their orbital periods do not have simple ratios, but they do have approximate resonances. These approximate resonances act as brakes. They prevent chaotic interactions. Consider Neptune and Pluto. Neptune and Pluto should collide mathematically. Their orbits overlap, but Pluto orbits the Sun 3 times while Neptune orbits twice. This 2-3 resonance keeps them separated. When Pluto approaches Neptune's orbital path, Neptune is never there. The resonance acts as a traffic cop, directing the 2 objects so they never meet. This is not accidental. The resonance formed over millions of years as Pluto and Neptune exchanged gravitational momentum, They eventually locked into a configuration where they could coexist. The system found its own stability. The inner solar system is more crowded and the resonances are more complex. But the principle is the same. The planets have negotiated their way into a configuration where they can coexist without catastrophically disrupting each other. This configuration is not the only possible one. Computer simulations show that planetary systems with different masses, different starting positions, and different orbital inclinations can also be stable. Some collapse, some become chaotic, some settle into configurations that are radically different from ours. But the ones that are stable, the ones that persist for billions of years, all share a common feature. They have found a resonance, a pattern, a rhythm that allows each planet to keep the others in check. The solar system is not just a gravitational negotiation. Each planet plays a specific role in maintaining the stability of the whole. Jupiter is the bouncer. Jupiter is massive enough that its gravity dominates the inner solar system. Any asteroid or comet that drifts too close to Jupiter's orbit is either scattered outward or pulled inward toward the Sun. This has the effect of clearing the inner solar system of large debris. Without Jupiter, the inner solar system would be far more crowded. Earth would have been bombarded by asteroids far more frequently than it actually was. Complex life may never have emerged. But Jupiter is also dangerous. Its gravity creates the asteroid belt. When Jupiter migrated outward early in the solar system's history, it scattered asteroids in all directions. Most were ejected. The ones that remained became the asteroid belt. Jupiter is a protector and a destroyer. It keeps the inner solar system habitable by clearing debris. But it is also the reason that debris exists at all. Saturn is the stabilizer. Saturn is less massive than Jupiter, but its gravitational influence is profound. Saturn and Jupiter interact in complex ways. When Jupiter tugs inward on the inner planets, Saturn's gravity tugs back. This back and forth creates a kind of dynamic balance. Additionally, Saturn's gravity helps shape the asteroid belt. The Kirkwood gaps, regions of the asteroid belt where almost no asteroids exist, are caused by resonances between asteroid orbits and Saturn's orbit. Asteroids in certain orbital periods are tugged by Saturn until they drift out of the belt entirely. Uranus and Neptune are the distant anchors. Uranus and Neptune are far enough from the Sun that they do not directly interact with the inner planets very often, but their gravity provides a gravitational boundary. They define the edge of the Sun's sphere of influence. They catch comets and asteroids that drift too far outward. The inner planets stabilize each other. Mercury, Venus, Earth, and Mars are small enough that their individual gravitational influences are modest, but together they create a system of overlapping gravitational influences that keep each other from drifting. Earth's gravity tugs on Venus. Venus tugs on Mercury. The four inner planets are in constant negotiation, trading tiny amounts of momentum over millions of years. This is why planetary migration in the early solar system was so dramatic. When Jupiter and Saturn migrated outward, they scattered the inner planets violently. The configuration the inner planets settled into, the one we see today, is the result of billions of collisions, ejections, and gravitational tugs that occurred in the first 100 million years of the solar system's existence. There is a deep question lurking beneath all of this. How stable is the solar system actually? The answer is less stable than we used to think. For centuries, astronomers believed the solar system was perfectly stable. Newton's laws seemed to guarantee it. Gravity was orderly. Orbits were predictable. But in the 1980s, chaos theory revealed a problem. Even simple gravitational systems with just three bodies can become chaotic. Tiny changes in starting conditions can lead to wildly different outcomes. If you perturb the position of Mercury by a millimeter, its orbit a billion years in the future might be completely different. The solar system is such a system. The orbits of the planets are mathematically chaotic. This does not mean they are random, they follow Newton's laws perfectly, but it means they are unpredictable over long timescales. We can predict where Mercury will be in 100 years. We cannot predict where it will be in a billion years because the precision required would exceed the precision we can measure. Computer simulations suggest that the solar system will remain stable for at least another 10 billion years, but there is no guarantee. A close encounter with a passing star, a collision with a rogue planet wandering through the galaxy, or simply the chaotic evolution of the orbits themselves could eventually destabilize the system. In fact, some simulations suggest that Mercury itself may eventually be ejected from the solar system or may spiral into the sun. The probability is low, perhaps 1% over the next 5 billion years, but it is not zero. This is what it means for a system to be dynamic. It is not fragile. The solar system has persisted for 4.6 billion years, but it is not eternal. It is a process, not a structure. It is held together by balance, not by law. The solar system is not unique. Astronomers have discovered thousands of exoplanet systems, planets orbiting other stars. These systems reveal the range of possibilities. Some exoplanet systems are radically different from ours. Hot Jupiters, gas giants in orbits closer to their stars than Mercury is to the Sun, are common around other stars, but do not exist in our solar system. Some systems have 10 or more planets. Some have planets whose masses vary wildly. But the stable systems, the ones that have likely persisted for billions of years, share common features with our solar system. A central star whose gravity dominates. Planets whose masses are spread across multiple objects rather than concentrated in one. Orbital configurations that avoid resonances that would destabilize the system. A depletion of small bodies in the inner region, similar to our asteroid belt. The solar system is not a fluke. It is a stable configuration that emerges when a particular set of conditions are met. The conditions are not unique, but they are not universal either. Many planetary systems collapse into chaos or have one planet ejected. Ours did not. This is partly luck, partly physics, partly the fact that Jupiter was massive enough to dominate, but not so massive that it destabilized everything else. The solar system as a system teaches us something about stability in general. Stability is not a default state. It is an achievement. It requires balance. It requires components that interact in ways that reinforce each other's positions rather than undermining them. The solar system is stable because Jupiter clears debris, because Saturn stabilizes Jupiter, because the inner planets are small enough to be manageable, but numerous enough to reinforce each other, because the resonances that formed early on persist and keep the planet separated. Remove any of these components and the system becomes unstable. Add too much mass in one place and the system becomes unstable. Change the starting configuration slightly and the system might have collapsed into chaos in the early solar system, ejecting planets or causing collisions. The solar system we see is not inevitable. It is contingent. It is the result of billions of years of negotiation between massive objects, each tugging on the others, each finding its place in a configuration that works. This is not a law of physics. This is emergence. This is what happens when you have multiple components with conflicting interests, and they find a way to coexist anyway. The same principle applies to ecosystems, to economies, to political systems. Stability emerges from balance. It requires multiple actors with some degree of independent power. It requires them to interact in ways that are dynamic but not chaotic. The solar system is a reminder that the universe is not orderly and static. It is dynamic and precarious. It is held together by forces that are constantly negotiating, constantly tugging, constantly trading momentum across the void. And the fact that it has lasted 4.6 billion years is not a sign of eternal stability. It is a sign of remarkable fragile balance. A galaxy is not a collection of stars. It is a negotiation between gravity and motion. 200 billion stars orbit a single point, a supermassive black hole at the galactic center. They move at tremendous speeds. They should fly apart. The black hole should be too small to hold them. The math says the galaxy should not exist, but it does. This is what it means for something to be a system at the galactic scale. Every galaxy has a center. At the center of most large galaxies sits a supermassive black hole. The Milky Way's supermassive black hole is called Sagittarius A star. It has a mass of about 4 million suns. 4 million suns compressed into a region smaller than the orbit of Mercury. The gravity of Sagittarius A star is immense. It is strong enough that not even light can escape from directly above the event horizon. It is strong enough that stars orbiting within a few light years of the galactic center move at speeds of thousands of kilometers per second. But here is the strange part. The supermassive black hole at the center of a galaxy does not hold the galaxy together. The stars in the outer regions of the Milky Way, stars that are tens of thousands of light years from the galactic center, orbit at speeds that are far too fast to be explained by the gravity of the central black hole alone. If the only mass in the galaxy were the stars we can see, plus the supermassive black hole at the center, the outer stars should fly apart. They do not. This is the dark matter problem. And it is the key to understanding how galaxies work as systems. Galaxies are surrounded by a halo of invisible matter. We cannot see this matter. We cannot touch it. We can only infer its existence from its gravitational effects. This is dark matter. The dark matter halo extends far beyond the visible disk of a galaxy. It surrounds the galaxy like an invisible sphere. It contains more mass than all of the visible stars combined, roughly 5 to 10 times more mass. For every kilogram of ordinary matter we can see, there are 5 to 10 kilograms of dark matter we cannot. The dark matter halo is what holds galaxies together. Without the dark matter halo, the Milky Way would be unstable. The outer stars would fly away. The galaxy would disperse into space. The reason galaxies persist, the reason they have not flown apart over billions of years, is that they are embedded in massive halos of dark matter whose gravity provides the gravitational anchor. We do not know what dark matter is. It is not atoms. It is not molecules. It does not interact with light. The leading hypothesis is that it is composed of exotic particles that barely interact with ordinary matter at all. These particles pervade the galaxy. They are everywhere. They are passing through you right now. But for the purposes of understanding how galaxies work as systems, what matters is not what dark matter is, but what it does. It provides the gravitational framework that holds the visible galaxy in place. The galaxy is therefore not what we see when we look at the sky. The galaxy is mostly invisible. The stars we see are the thin tracery of visible matter orbiting within a vast sphere of dark matter whose presence we infer only from its gravitational effects. This is a humbling reversal. We thought we understood what galaxies were made of. It turns out we were only seeing the minority component, the visible part. The majority of the galaxy's mass is dark, invisible, inferred. The way we discovered dark matter was through the rotation curve of galaxies. A rotation curve plots the orbital speed of stars as a function of their distance from the galactic center. If a galaxy were held together only by the gravity of the visible stars and the central black hole, the rotation curve should follow a specific shape. Stars close to the center should orbit quickly, and stars farther out should orbit more slowly, in a way that matches Newton's laws. This is what we expected. This is not what we observed. Instead, the rotation curves of galaxies are flat. Stars close to the center orbit at a certain speed. Stars much farther out orbit at roughly the same speed. The rotation curve is nearly constant across the entire disk of the galaxy. This is impossible if the only mass is the visible stars. It is only possible if there is additional mass, dark matter, distributed throughout the halo, providing extra gravity at large distances. The rotation curve is therefore a map of the dark matter distribution. It shows where the dark matter is and how much of it there is. And it shows that the visible galaxy, the stars, the gas, the dust that we can see, is embedded in a much larger structure of invisible matter. This is the first principle of galaxies as systems. The visible structure is supported by an invisible infrastructure, but the galactic center is not invisible. It is one of the most violent and dynamic places in the Milky Way. Sagittarius. A star, the supermassive black hole at the center of the Milky Way, is not a quiet object. Stars orbit it at speeds of thousands of kilometers per second. Every few years, a star gets close enough to the black hole that the tidal forces, the difference in gravity between the near side and far side of the star, tear the star apart. The debris spirals into the black hole, releasing tremendous energy. Additionally, the region around the galactic center is crowded with stars. Millions of stars orbit within a few light years of the black hole. Their mutual gravity creates a dense stellar system. Collisions between stars are far more common near the galactic center than in the outer regions of the galaxy. The galactic center is also a source of powerful jets and outflows. Material falling into the black hole releases energy that blasts outward, heating the surrounding gas and expelling it from the galaxy. These outflows can extend for thousands of light years. What is happening at the galactic center? The galactic center is the place where the galaxy is most alive. It is the engine of galactic evolution. The Milky Way rotates, not in the way the Earth rotates, with the entire disk turning rigidly like a phonograph record, but as a differential rotation. The inner regions rotate faster. The outer regions rotate more slowly. A star near the galactic center completes an orbit around the galactic center in a few million years. A star like the Sun, located about 26,000 light years from the galactic center, takes about 230 million years to complete one orbit. This differential rotation is important. It prevents the galaxy from flying apart. Consider, the stars in a galaxy are moving at different speeds, and they are distributed across space. The gravity of the dark matter halo provides the force that keeps them in orbit. But the details matter. A star that is moving too slowly for its distance will fall toward the galactic center. A star that is moving too fast will escape outward. Only stars moving at the right speed for their distance, the velocity that balances the gravitational pull from the dark matter halo and the visible matter, stay in stable orbits. Over billions of years, this creates order. The galaxy settles into a configuration where most stars are in stable orbits. Stars that are moving too fast or too slowly gradually settle into more stable configurations through repeated gravitational interactions with other stars.
The result is the rotation curve we observe, a relatively flat distribution where most stars orbit at speeds that are stable for their distance. This is stability through velocity distribution. It is not static, it is dynamic. But the dynamics are constrained in a way that prevents chaos. The Milky Way is a spiral galaxy. It has a flat disk with spiral arms extending outward from the galactic center, like the arms of a pinwheel. For a long time, astronomers thought the spiral arms were made of stars that physically orbited the galactic center together, like rigid spokes. But this creates a problem. If stars in the inner regions orbit faster than stars in the outer regions due to differential rotation, the spiral arms would wind tighter and tighter over time. After a few billion years, the arms would be wound so tightly that they would disappear. But we observe spiral arms in galaxies that are billions of years old. The solution is the density wave theory. The spiral arms are not made of the same stars. Instead, they are density waves, regions of slightly higher density that rotate around the galactic center. Stars move through the density waves. A star enters a spiral arm, experiences slightly stronger gravity, slows down a bit, and then exits the spiral arm on the other side. The spiral arms are like traffic jams on a highway. The jam does not move at the same speed as the cars. Cars enter the jam, slow down, and then exit. The jam persists, but it is not made of the same cars. Similarly, spiral arms persist in galaxies, but they are not made of the same stars. The arms are standing waves in the gravitational field of the galaxy. This is remarkable. It means that the large-scale structure of a galaxy, its spiral arms, is not a static structure made of individual stars. It is a dynamic pattern, a wave in the distribution of matter that can persist for billions of years, even though the individual components are constantly moving. This is what emergence looks like at the galactic scale. Galaxies are more stable than solar systems in some ways. A galaxy contains so many stars that small perturbations average out. The loss of a single star is negligible. The gravitational influence of a few stars on the overall dynamics is insignificant. But galaxies can be destabilized. The most dramatic destabilization comes from collisions with other galaxies. When two galaxies collide, they do not simply pass through each other. Galaxies are mostly empty space. If you scaled down a galaxy to the size of a room, the stars would be smaller than grains of sand, separated by distances of many meters. The probability of two stars actually colliding during a galactic merger is almost zero. But the gravitational interaction between the two galaxies is enormous. When two galaxies pass through each other, their mutual gravity distorts both of them. Stars are pulled out of their orbits. The orderly rotation of the galactic disk is disrupted. Spiral arms can be stretched and torn. The dark matter halos of the two galaxies interact, exchanging momentum and energy. If the two galaxies are moving slowly relative to each other, they can merge. Their dark matter halos combine. Their stars mix. Over the course of 1 billion years, the system settles into a new configuration. Often, the result is an elliptical galaxy, A galaxy with no spiral arms, with stars distributed in a roughly spherical shape rather than a disk. Elliptical galaxies are the result of galactic collisions. They are merger remnants, and they tell us something important. Galactic systems are not permanent structures. They can be dramatically rearranged by gravitational interactions with other galaxies. The Milky Way itself has collided with smaller galaxies repeatedly. The Sagittarius dwarf galaxy, a small elliptical galaxy, is in the process of being absorbed by the Milky Way right now. Its stars are being stripped away and added to the Milky Way's halo. In a few billion years, the Sagittarius dwarf galaxy will cease to exist as a separate entity. It will be incorporated into the Milky Way. And in about 5 billion years, the Milky Way will collide with the Andromeda Galaxy, our nearest large neighbor. The collision will be slow by human standards, but fast by cosmic standards. The two galaxies will pass through each other. Their disks will be disrupted. Over the course of a few billion years, they will merge into a single, larger galaxy. Astronomers call the result the Milkomeda. A galaxy is a system where each component plays a role in maintaining the stability of the whole. The dark matter halo provides the gravitational anchor. Without the dark matter halo, the galaxy would not hold together. The visible matter alone is not sufficient to explain the orbital velocities of the stars. The dark matter halo provides the additional gravity needed to keep stars in stable orbits across the entire disk of the galaxy. The supermassive black hole at the center regulates the galaxy's evolution. The black hole is too small to gravitationally dominate the entire galaxy, but its presence is profound. As material falls into the black hole, it releases energy. This energy heats the surrounding gas, which can prevent further gas from falling into the black hole. This acts as a thermostat, regulating how quickly the galaxy can form new stars. Additionally, the jets and outflows from the black hole can expel gas from the galaxy entirely, further regulating star formation. The black hole's influence on the galaxy extends far beyond its immediate vicinity. The disk of visible matter provides the structure. The stars, gas, and dust in the galactic disk are what we see when we observe a galaxy. They are the tracery, the visible component. But they also provide the structure that defines the galaxy's shape, the spiral arms, the bulge at the center, the thin disk extending outward. The spiral arms organize star formation. The density waves that create spiral arms move more slowly than the stars. When a cloud of gas enters a spiral arm, it slows down. This compression can trigger the collapse of the gas cloud into new stars. Spiral arms are therefore regions of active star formation. They are where new stars are born. This is why spiral galaxies tend to have bright blue stars in their spiral arms. These are young, massive stars that have not yet lived out their short lives. The outer regions of the disk, outside the spiral arms, have older, redder stars. Smaller satellite galaxies provide perturbations and inputs. Large galaxies are surrounded by smaller satellite galaxies. The Milky Way has dozens of satellite galaxies, including the large and small Magellanic Clouds. These satellites orbit the large galaxy. Their gravity tugs on the large galaxy, creating tidal effects that can trigger bar formation, warp the disk, or launch tidal streams of stars into the galactic halo. The satellites also fall slowly toward the large galaxy, gradually losing orbital energy. Eventually, they will be absorbed. When they are absorbed, their stars are incorporated into the large galaxy, increasing its mass and possibly triggering a burst of star formation. All of this happens on timescales that are almost incomprehensibly long. The Milky Way is about 13.6 billion years old. It formed a few hundred million years after the Big Bang. It has been evolving for over 13 billion years. A single orbit of the Sun around the galactic center takes about 230 million years. This is called a galactic year. In the entire age of the Milky Way, the Sun has completed only about 60 galactic years. The dinosaurs on Earth lasted about 165 million years, less than one galactic year. The entire history of human civilization, from the emergence of writing to today, spans about 5,000 years, 1/46th of a galactic year. From the perspective of the galaxy, the existence of human civilization is instantaneous. We live in a moment that is negligible from the galactic point of view. But even though galactic timescales are vast, change does happen. Stars are born and die, spiral arms rotate, satellite galaxies are absorbed. The disk is warped by tidal interactions. The black hole at the center consumes material and regulates star formation. Over billions of years, the galaxy evolves. It is not static. It is a process. The galaxy teaches us something about systems at extreme scales. A system does not need to have rigid boundaries or fixed components to be stable. The Milky Way contains 200 billion stars, all orbiting at different speeds, all distributed across space, all moving independently. Yet the system as a whole is stable. It has persisted for 13 billion years without flying apart. This stability emerges from the interaction of many components. The dark matter halo provides a gravitational potential well. The stars occupy orbits within that well. The supermassive black hole regulates the flow of energy through the system. Spiral arms organize the distribution of matter. No single component is essential in the way that the Sun is essential to the solar system. Remove Jupiter, and the solar system becomes unstable. But remove a single star from the Milky Way, and the galaxy barely notices. The system is robust to the loss of individual components because it contains so many components. This is scale invariance in a sense. The principles that make the solar system stable, gravity, orbital mechanics, resonance, are the same principles that make the galaxy stable. But at the galactic scale, stability emerges from numbers. With enough stars, statistical effects smooth out local perturbations. Another principle: a system can be dynamic and stable simultaneously. The Milky Way is not unchanging. Stars are born and die. Gas is expelled and accreted. Satellite galaxies are absorbed. Spiral arms rotate, yet the system persists. Dynamism and stability are not opposites. They are aspects of the same process. The galaxy also teaches us that systems exist within systems. The stars orbit the galaxy. The galaxy orbits within a galaxy cluster. The galaxy cluster is part of a supercluster. Each level of organization has its own dynamics, its own timescales, its own forms of stability and instability. Understanding the galaxy requires understanding how it sits within the larger cosmic context. The Milky Way is a large spiral galaxy. It is about 100,000 light-years in diameter. It contains about 200 billion stars. It is embedded in a dark matter halo that extends to about 300,000 light-years. By galactic standards, the Milky Way is not exceptional. It is not the largest galaxy. The elliptical galaxy IC 1101 is about 4 million light-years in diameter and contains about 100 trillion stars. It is not the smallest. Dwarf galaxies contain a few million stars. It is a typical large spiral galaxy. But it is our galaxy. It is what we are embedded in. Understanding how the Milky Way works as a system is the foundation for understanding how galaxies work in general. The Milky Way contains everything we know to exist. Every star we see with the naked eye is part of the Milky Way. Every exoplanet we have discovered orbits a star in the Milky Way. The Andromeda Galaxy, the The nearest large galaxy to us is about 2.5 million light-years away, 25 times farther than the diameter of the Milky Way. We are not at the center of the galaxy. We are not in a special location. We are on the outskirts of a spiral arm, about 26,000 light-years from the galactic center, 50,000 light-years from the galactic edge. We are insignificant from the galactic point of view. And yet, from our perspective, the Milky Way is everything. It is the entire universe as we knew it for all of recorded history, until only about a century ago when we realized that other galaxies existed beyond it. This shift in perspective, from seeing the Milky Way as the universe to seeing it as one typical large galaxy among billions, is one of the most profound shifts in human understanding. The Milky Way will not remain as it is. In a few billion years, it will collide with Andromeda. The collision will unfold over a timescale of about 2 billion years. During this time, the two galaxies will pass through each other. Their disks will be disrupted. Their dark matter halos will merge, and the system will eventually settle into a new configuration, a larger elliptical galaxy, or possibly a new spiral galaxy if the collision is gentle enough. The Sun will likely survive the collision. It will be ejected from its current orbit and thrown into a different part of the galaxy, but it will not be destroyed. Earth may or may not survive. If the Sun is ejected far from the galactic center, it will find itself in a region of space where planets can still orbit. But if the collision is violent, Earth's orbit could be disrupted. From a galactic perspective, the collision with Andromeda is not a catastrophe. It is simply the next phase of the galaxy's evolution. Galactic collisions are common. They have happened repeatedly in the history of the Milky Way. In a sense, the Milky Way exists today because it has collided with and absorbed many smaller galaxies over the course of its 13 billion-year existence. After the collision with Andromeda, the newly merged galaxy will continue to evolve. It will absorb more satellite galaxies. Its stars will continue to be born and die. Its spiral arms will rotate. Its supermassive black hole will continue to regulate its evolution. Eventually, in the very distant future, trillions of years from now, the galaxy will wind down, stars will burn out, the expansion of the universe will carry other galaxies farther and farther away. The newly merged Milk-Dromeda galaxy will find itself increasingly isolated in an expanding cosmos. But that is far in the future. For now, the Milky Way persists as a dynamic system, held together by the invisible web of dark matter, organized by its supermassive black hole, structured by its spiral arms, populated by its hundreds of billions of stars. The universe is made of dark matter. Everything we see, every star, every galaxy, every atom in your body is a thin tracery of ordinary matter clinging to the skeletal structure of dark matter. Dark matter provides the framework. Ordinary matter fills in the details. This is the inverted reality of modern cosmology. We are not the substance of the universe. We are the decoration. If you look up at the night sky, it appears random. Stars are scattered across space. Galaxies are distributed seemingly haphazardly. There is no obvious pattern. But if you zoom out, if you map not individual galaxies, but clusters of galaxies, superclusters, the large-scale structure of the universe itself, a pattern emerges. Galaxies are not uniformly distributed throughout space. They are clumped. They are organized into clusters. Clusters are organized into superclusters. Superclusters are organized into filaments. Filaments surround vast voids where almost no galaxies exist. The universe has structure, large-scale cosmic structure. This structure looks like a web. Imagine strands of material spread across space, forming a three-dimensional lattice. Galaxies cluster along the strands. The spaces between the strands are nearly empty. This is called the cosmic web. For decades, astronomers had no explanation for why the cosmic web existed. Gravity should have spread matter evenly throughout the universe. The universe should be uniform. But it is not. The answer is dark matter. The cosmic web is made of dark matter. To understand how dark matter scaffolds the universe, we need to go back to the beginning. The Big Bang happened about 13.8 billion years ago. At the moment of the Big Bang, the universe was incredibly hot and dense. Matter and radiation were indistinguishable. Space itself was expanding at an unimaginable rate. Within the first fraction of a second, the universe expanded and cooled. Fundamental particles formed. Quarks combined into protons and neutrons. Within the first few minutes, some of these protons and neutrons combined into the first atomic nuclei, mostly hydrogen and helium, with traces of lithium. But here's what happened to dark matter. Dark matter decoupled from ordinary matter almost immediately. Within a fraction of a second of the Big Bang, dark matter stopped interacting with ordinary matter. From that moment on, dark matter and ordinary matter evolved separately. Ordinary matter, being charged and interacting with radiation, was pushed around by radiation pressure. It stayed hot. It resisted clumping. It was difficult for gravity to pull ordinary matter together into dense structures because radiation was pushing it apart. But dark matter, being invisible and non-interacting, was not affected by radiation pressure. Dark matter could respond freely to gravity. Gravity could pull dark matter together into clumps. And so, in the first moments of the universe, dark matter began to collapse under its own gravity. It formed clumps. It formed halos. It began to organize itself into structures. Ordinary matter, meanwhile, was still being pushed around by radiation. It could not easily form dense structures. This is a crucial point. The universe's large-scale structure was sculpted by dark matter in the first moments after the Big Bang, when ordinary matter was still locked in radiation pressure. About 380,000 years after the Big Bang, something momentous happened: recombination. The universe had cooled enough that protons and electrons could combine to form neutral hydrogen atoms. Before this moment, the universe was a plasma, a soup of charged particles. Radiation could not pass through a plasma. The universe was opaque. After recombination, the universe became neutral. Neutral atoms do not interact with radiation as strongly as charged particles do. Radiation could finally travel freely through space. The universe became transparent. And here is the key. When the universe became transparent, radiation pressure released its grip on ordinary matter. Ordinary matter was finally free to respond to gravity. But ordinary matter did not start from scratch. Gravity had already been sculpting dark matter for 380,000 years. Dark matter had already formed halos and clumps. Ordinary matter fell into these pre-existing structures. It collapsed into the gravitational wells that dark matter had created. This is the mechanism. Dark matter created the scaffolding. Ordinary matter filled in the scaffolding. Without dark matter having already organized itself into structures, ordinary matter would have taken much longer to collapse into galaxies and clusters. The universe would have evolved differently. It might not have formed galaxies at all, or only very slowly, after billions of years. But because dark matter had already done the work of organizing space into structures, ordinary matter could rapidly fall into those structures and form galaxies. The universe we see today, with galaxies and clusters and the cosmic web, is the direct result of dark matter's early scaffolding work. Zoom back into the present day. Focus on a single galaxy, the Milky Way, or any large spiral galaxy. The galaxy is surrounded by a halo of dark matter. This halo extends far beyond the visible disk of stars. The halo is roughly spherical, centered on the galaxy's center, extending outward to distances of hundreds of thousands of light years. The dark matter halo is not uniform. It is densest at the center, near the galactic nucleus. It becomes more diffuse as you move outward. But here's the crucial point. The dark matter halo does not exist in isolation. It is connected to the larger cosmic web. Dark matter filaments extend outward from the galaxy, connecting it to neighboring galaxies and galaxy clusters. The dark matter halo around a galaxy is a local concentration of a global structure. Ordinary matter, the stars, gas, and dust that make up the visible galaxy, is embedded within this dark matter halo. The stars orbit within the gravitational potential well created by the dark matter. The gas is held in place by the dark matter's gravity. The entire visible galaxy is cradled within the dark matter structure. This is why galaxies are where they are. Galaxies form where dark matter has accumulated. Ordinary matter falls into the dark matter wells. Stars and gas accumulate in these locations. Galaxies emerge. If you could see dark matter directly, the universe would look very different from how it appears when you look only at ordinary matter. You would see a vast network of dark matter filaments with concentrations at certain points. Ordinary matter would appear as tiny luminous specks scattered throughout this structure, following its geometry. The formation of galaxies is a process that is still not completely understood, but the broad outlines are clear and dark matter is central to every step. In the early universe, after the cosmic web had begun to form, ordinary matter fell into the dark matter wells. Gas accumulated in these wells, forming clouds. These clouds were pulled deeper into the wells by gravity. As the gas became denser and hotter, it began to form stars. But here is where dark matter plays a crucial regulatory role. Dark matter provides the gravitational anchor that keeps the gas from flying apart. Without dark matter, the gravity of the ordinary matter alone would not be sufficient to hold the gas together as stars formed. The galaxy's dark matter halo provides the potential well. The galaxy's ordinary matter forms within that potential well. The supermassive black hole at the galactic center provides additional regulation and energy feedback. But without the dark matter halo, the galaxy would not have a strong enough gravitational anchor. The gas would be dispersed, star formation would be inefficient, the galaxy would not reach the size and mass that we observe. Dark matter therefore determines the gravitational scale at which galaxies can form. A galaxy is as large as it is because its dark matter halo is as large as it is. Zoom out further. Focus not on individual galaxies, but on clusters of galaxies. A galaxy cluster is a collection of hundreds or thousands of galaxies bound together by gravity. The largest clusters contain more than 1,000 galaxies. The Milky Way is part of the local group, which contains about 80 galaxies, though only a few are large. The local group is part of the Virgo supercluster, which contains tens of thousands of galaxies. Galaxy clusters are the largest gravitationally bound structures in the universe. Everything within a cluster, all the galaxies, all the gas between the galaxies, all the dark matter, is held together by gravity. But here is the puzzle. When you add up the mass of all the visible galaxies in a galaxy cluster, the total mass is not enough to hold the cluster together. The galaxies should be flying apart. The cluster should be unstable. The solution, dark matter. Galaxy clusters contain far more dark matter than ordinary matter. The dark matter halos of the individual galaxies merge together into a larger dark matter structure. This larger dark matter halo holds the cluster together. Without dark matter, galaxy clusters would not exist. The galaxies would disperse into space. The universe would not have the structure we observe. Zoom out even further. Look at the universe on the largest scales, the cosmic web, the filaments and voids that structure the universe, is made of dark matter. Ordinary matter traces the cosmic web, but it does not create it. Galaxies form along the filaments because the filaments are concentrations of dark matter. Gas accumulates along the filaments because dark matter's gravity pulls it there. Stars form in the accumulating gas. But if you could remove all the ordinary matter from the universe, all the stars, all the gas, all the atoms, the cosmic web would still be there. Dark matter would still define the structure. The cosmic web is the scaffolding. Ordinary matter is the building constructed on that scaffolding. This is a profound inversion of intuition. We think of matter as the substance of the universe. Stars are made of matter. Galaxies are made of matter. We are made of matter. But the universe is not structured by ordinary matter. It is structured by dark matter. Ordinary matter is a passenger on the framework that dark matter provides. Dark matter is not randomly distributed. It is clumped and concentrated in specific places. The highest concentrations of dark matter are at the centers of galaxy clusters. These are the nodes of the cosmic web. Filaments of dark matter extend outward from these nodes, connecting one node to another. Between the nodes and filaments are vast voids, regions of nearly empty space where almost no galaxies exist and almost no dark matter accumulates. This is the large-scale structure of the universe: nodes, filaments, and voids. The nodes are galaxy clusters. The filaments connect the clusters. The voids are empty. But even in the voids, dark matter is not completely absent. Dark matter permeates all of space, but the density is much lower in the voids than in the filaments and nodes. This distribution of dark matter determines where ordinary matter can accumulate. Galaxies form in the filaments and nodes. Very few galaxies form in the voids. The structure of the universe as we observe it, with galaxies concentrated along filaments, with empty voids between them, is a direct consequence of how dark matter is distributed. The cosmic web was not created all at once. It evolved over time. In the very early universe, dark matter was nearly uniformly distributed. But tiny density fluctuations, quantum fluctuations that existed at the moment of the Big Bang, were amplified by gravity. Over billions of years, these tiny fluctuations grew into the massive structures we observe today. Dark matter clumped where the density was slightly higher. It became more sparse where the density was slightly lower. Ordinary matter followed, accumulating where dark matter was dense, forming galaxies and clusters. This is called gravitational instability. A universe that starts nearly uniform can, under gravity, develop increasingly pronounced structure. The structure grows over time. Clumps become more clumped, voids become more empty. By the present day, about 13.8 billion years after the Big Bang, the structure is well developed. The cosmic web is clearly defined. Galaxies are concentrated along filaments. Voids are vast and nearly empty. But this process is not finished. The universe is still evolving. Structures are still growing. Galaxy clusters are still merging. The cosmic web is still being refined. In the very distant future, trillions of years from now, the structure may evolve further. But for the foreseeable future, the cosmic web will remain the defining feature of the universe's large-scale structure. Why does this matter? Why is dark matter's role as cosmic scaffolding important? It matters because it reveals something fundamental about how the universe works. For most of human history, we believed that ordinary matter, the matter we are made of, the matter we can see and touch, was the substance of reality. Everything else was secondary, derivative, or illusory. The discovery of dark matter inverted this assumption. Ordinary matter is not the substance of the universe. It is a thin decoration on a much larger framework. Understanding dark matter as cosmic scaffolding means understanding that 1. We are not central to the universe's structure. The universe is not built from atoms and molecules that assemble into larger structures. The universe is built from dark matter that provides the gravitational framework and ordinary matter that fills in the details. We are filling in the details. We are not the foundation. 2. The universe's architecture was determined before ordinary matter could even form. Dark matter organized itself into the cosmic web in the first moments after the Big Bang, when ordinary matter was still locked in radiation. By the time ordinary matter became free to form structures, the cosmic web was already in place. Ordinary matter had no choice but to follow the pathways that dark matter had created. This means that the existence of galaxies, clusters, and the cosmic web was determined by the early universe behavior of dark matter. Ordinary matter is following a script that was written in the first moments of cosmic history. 3. The universe is fundamentally invisible. Most of the universe is dark matter. We cannot see it. We cannot touch it. We can only infer its existence from its gravitational effects. The universe we inhabit is mostly made of something we do not understand and cannot directly perceive. This is a humbling realization. It suggests that our understanding of the universe is incomplete. There is far more to reality than what we can observe directly. The metaphor of scaffolding is apt. Consider a building under construction. The scaffolding is the temporary framework that holds everything in place while the building is being constructed. The scaffolding provides the structure. The actual building, the walls, the floors, the rooms, is built on top of the scaffolding. Once the building is complete, the scaffolding is still there, but we do not see it. We see the building. We use the building. We live in the building. We forget about the scaffolding, but the scaffolding is still essential. Without it, the building could never have been constructed. The building's shape, its size, its location, all of these are determined by the scaffolding. The universe is similar. Dark matter is the scaffolding. Ordinary matter, galaxies, stars, atoms, us, is the building constructed on that scaffolding. We see the building. We study the building. We live in the building. We forget about the scaffolding. But the scaffolding is essential. Without it, the building could never have been constructed. The universe's structure, its size, its shape, all of these are determined by dark matter. Let us follow a specific strand of this cosmic scaffolding and see how ordinary matter accumulates along it. Imagine a dark matter filament extending through space. The filament is not solid. It is a concentration of dark matter distributed across a region of space, perhaps 100 million light-years long and 10 million light-years thick. Dark matter is more concentrated along the filament's spine and less concentrated at its edges. Now imagine ordinary matter, mostly primordial hydrogen and helium gas left over from the Big Bang, falling into the gravitational potential well created by this dark matter filament. The gas cannot fall all the way to the spine of the filament at once. As it falls, it collides with other gas. The collisions slow it down. The gas settles into a disk around the filament's spine, like an accretion disk around a black hole. Within this disk of gas, small density fluctuations grow. One region becomes slightly denser than its surroundings. Its gravity increases. It pulls in more gas. It becomes denser still. Over tens of millions of years, this region collapses into a galaxy. Multiple such regions collapse into multiple galaxies. These galaxies cluster together along the dark matter filament. A line of galaxies forms, strung along the filament like beads on a string. This is what we observe when we map the large-scale structure of the universe. Galaxies are not randomly distributed. They are concentrated in filaments. The filaments form the cosmic web, and the filaments exist because dark matter is concentrated along them. Between the filaments are voids. Voids are regions of space where both dark matter and ordinary matter are sparse. A typical void might be 100 million light-years across. Within a void, there are very few galaxies. The void is mostly empty. Why are voids empty? Because dark matter is not concentrated there. If dark matter were uniformly distributed, then ordinary matter would be uniformly distributed as well, and galaxies would be uniformly distributed. The universe would be homogeneous, but dark matter is not uniformly distributed. It is clumped. The clumping creates regions where dark matter is dense, the filaments and nodes, and regions where dark matter is sparse, the voids. Ordinary matter follows. Galaxies form in the dense regions. Voids remain empty. The existence of voids is therefore a consequence of dark matter's non-uniform distribution. Voids are not empty by accident. They are empty because there is not enough dark matter there to pull ordinary matter together into galaxies. This creates a feedback loop. Dark matter clumps in certain places. Ordinary matter falls into those clumps. Galaxies form. More dark matter accumulates in those regions through gravitational attraction of the dark matter itself. The density contrast between the clumped regions and the sparse regions grows larger over time. The voids do not remain empty by chance. They become increasingly empty as time goes on. The cosmic web has not always been as well defined as it is today. In the very early universe, just after recombination, the density fluctuations that would eventually grow into the cosmic web were tiny. The universe was nearly uniform. The variations in dark matter density were only about 1 part in 100,000. But gravity amplifies these variations. A region that is slightly denser than average pulls in more matter. It becomes denser still. Its gravity increases. It pulls in even more matter. This is exponential growth. Over billions of years, tiny variations grow into vast structures. By the present day, the density variations are enormous. The densest regions, galaxy clusters, have densities millions of times higher than the average. The sparsest regions, voids, have densities millions of times lower than the average. This growth of structure is ongoing. The universe is still evolving. Galaxies continue to cluster together. Filaments continue to concentrate. Voids continue to empty out. In the very distant future, the process may slow down or even reverse, depending on the properties of dark energy, which acts to accelerate the expansion of space. But for the foreseeable future, the cosmic web will continue to become more pronounced. Dark matter halos also play a crucial role in galaxy collisions. When two galaxies collide, their dark matter halos merge. The dark matter halos pass through each other, since dark matter barely interacts with anything. But as they pass through each other, they exchange gravitational momentum. The dark matter of one galaxy tugs on the dark matter of the other galaxy. This gravitational interaction slows down the collision. The two galaxies do not immediately merge. Instead, they enter a spiral, orbiting each other while slowly losing orbital energy. Over the course of 1 billion years or more, they gradually approach each other until they finally merge completely. Without dark matter, galaxy collisions would be much simpler. The ordinary matter would collide more directly. The merger would be faster and more violent. But with dark matter, galaxy collisions are more gradual and complex. The dark matter halos do most of the work of bringing the galaxies together. The ordinary matter, the stars and gas, follows along, gradually mixing as the galaxies spiral inward. This means that dark matter shapes not just the large-scale structure of the universe, but also the history of individual galaxies. Galaxies collide and merge in the way they do because of their dark matter halos. Think of dark matter filaments as channels through which ordinary matter can flow. Imagine a river. The river flows because gravity pulls water downhill, but the water can only flow in certain directions, along the path that gravity provides. A dark matter filament is similar. Ordinary matter, gas, dust, eventually galaxies, flows along the filament because gravity pulls it there. The filament is the path that gravity provides, but unlike water flowing in a river, ordinary matter does not flow smoothly along the filament. Instead, it accumulates, it pools, it forms into galaxies where the dark matter concentration is highest. Galaxies along a filament are not isolated, they are connected. They influence each other gravitationally. They are part of a larger cosmic structure, and the filament itself is not isolated. It is part of the cosmic web. It connects to other filaments at nodes, galaxy clusters. The entire network is interconnected through dark matter's gravity. To understand dark matter's role as cosmic scaffolding, imagine what the universe would be like without it. Without dark matter, galaxies would not form as easily. Ordinary matter's gravity alone would be insufficient to collapse gas into stars and galaxies on the timescales we observe. Galaxy formation would be slow and inefficient. Galaxies would be smaller and less massive. The gravitational potential wells that hold galaxies together would be weaker without dark matter's contribution. Galaxies could not grow as large. The cosmic web would not exist. Without dark matter to provide the scaffolding, ordinary matter would have no framework to organize around. Galaxies would be scattered randomly throughout space instead of concentrated in filaments. Voids would not exist. Voids are empty because dark matter is sparse there. Without dark matter's non-uniform distribution, there would be no reason for some regions to be empty and others to be crowded. The universe would be much more uniform. Density variations would grow more slowly without dark matter's early organization. The universe might still develop structure eventually, but it would take much longer. In essence, a universe without dark matter would be a universe without the large-scale structure we observe. It would be a much simpler, duller universe, probably too simple and dull to produce galaxies, stars, planets, and life. Dark matter is not a minor correction to our understanding of the universe. It is fundamental to the universe's structure. And yet, despite understanding dark matter's role as cosmic scaffolding, we still do not know what dark matter is. We know that dark matter provides most of the universe's mass, does not interact with light, is distributed non-uniformly, clumped into filaments and halos, responds to gravity and exerts gravitational effects, has shaped the structure of the universe since the earliest moments after the Big Bang. But we do not know what dark matter actually is. Is it a particle? Is it a field? Is it something we have not imagined yet? The particles that might make up dark matter, WIMPs, axions, sterile neutrinos, are still hypothetical. They have not been definitively detected. Physicists are searching for them, but the search has been frustratingly unsuccessful so far. It is possible that dark matter is something entirely unexpected. It is possible that we are missing something fundamental about how the universe works. But regardless of what dark matter is, we know what it does. It scaffolds the universe. It provides the framework on which ordinary matter builds. It is the architecture of cosmos. At the present moment, 13.8 billion years after the Big Bang, dark matter is distributed throughout the universe in a specific pattern. Dense concentrations at the centers of galaxy clusters, the nodes of the cosmic web, filaments of intermediate density connecting the nodes, extended halos around individual galaxies, much sparser density in the voids between filaments, a uniform baseline density permeating all of space. This distribution is the result of 13.8 billion years of gravitational evolution. It is the present state of a process that began with tiny quantum fluctuations in the first moments of the universe. The distribution is not static, it is changing. Filaments are becoming denser, nodes are becoming more concentrated, voids are becoming more empty. Galaxy clusters are merging. The contrast between dense and sparse regions is increasing. This evolution will continue. In billions of years, the cosmic web will be even more pronounced than it is today. The filaments will be thinner and more defined. The nodes will be more concentrated. The voids will be even more empty. But the fundamental structure, nodes, filaments, and voids, will remain. Dark matter will continue to provide the scaffolding on which ordinary matter depends. There is one more complication. The universe is expanding. Space itself is expanding. The distance between distant galaxies is increasing. This expansion is accelerating due to dark energy, a mysterious form of energy that pervades space and accelerates the expansion. How does dark matter respond to cosmic expansion? Dark matter does not resist expansion. As space expands, the dark matter expands with it. The filaments of the cosmic web are being stretched, the nodes are being pulled apart, but gravity works against expansion. Gravity pulls matter together. Within regions where dark matter and ordinary matter are clumped together, gravity can overcome expansion. Galaxy clusters, galaxies, and solar systems are not expanding because gravity is strong enough to hold them together against the expansion of space. But at very large scales, between galaxy clusters, along the filaments, expansion is winning. The filaments are being stretched. The universe is becoming less dense overall. This means that in the very distant future, the structure of the universe may change. If dark energy continues to accelerate expansion, the filaments may eventually be stretched so thin that they break apart. Galaxy clusters may become increasingly isolated. But this is far in the future. For the next hundreds of billions of years, the cosmic web will remain largely intact, providing the scaffolding for the continued existence of galaxies and clusters. Does dark matter exist in the solar system? Yes. Dark matter permeates all of space, including the solar system. Dark matter particles are passing through the Earth right now, passing through our bodies, passing through the sun. But the concentration of dark matter in the solar system is extremely low. The solar system is a tiny structure, and dark matter is distributed according to the large-scale structure of the universe. There is no significant dark matter halo around the solar system because the sun's gravity is too weak to attract and concentrate dark matter. However, there is a small background density of dark matter even in the solar system, the same background density that exists everywhere in space. This background dark matter has negligible effects on the motion of planets and spacecraft. But if we could somehow detect individual dark matter particles passing through the solar system, we would find them. They are there, part of the cosmic background of dark matter that fills all of space. What will happen to dark matter in the future? If the universe continues to expand, which it is, accelerated by dark energy, then dark matter will continue to be stretched and diluted. The average density of dark matter will decrease. Filaments will become thinner. Eventually, in the very distant future, trillions of years from now, the universe may become so dilute that the filaments disappear. Galaxy clusters may become isolated islands in an increasingly empty universe, but dark matter itself will not disappear. It will be scattered throughout an ever larger volume of space. It will continue to exert gravitational effects, but its effects will become increasingly dilute. In the context of cosmic timescales, this is the far future. For the next trillion years or more, the cosmic web will remain the dominant structure. But eventually, cosmic expansion may erase the cosmic web. There's a sense in which the cosmic web functions as a living system, not living in the sense of biology. The cosmic web is not alive, but it is dynamic. It is self-organizing. It responds to perturbations. It evolves. The cosmic web organizes itself through gravity. Dark matter clumps where the density is slightly higher. Ordinary matter follows. Galaxies form where dark matter concentrates most. The cosmic web also responds to perturbations. When two galaxy clusters collide, the impact is felt throughout the surrounding filaments. The filaments are warped and stretched. They gradually relax back to equilibrium. The cosmic web evolves on timescales of billions of years. Structure grows. Filaments become more defined. Nodes become more concentrated. In this sense, the cosmic web is like an organism growing and developing. It is not alive, but it has structure, organization, and evolution. Here is a final philosophical observation. Dark matter might be thought of as the substrate of reality. It is the underlying fabric on which everything else is built. Ordinary matter, atoms, molecules, life, exists on top of this substrate. Ordinary matter takes shapes and forms within the gravitational landscape created by dark matter. But ordinary matter is not the fundamental layer. Dark matter is the fundamental layer. It provides the stage on which the drama of the universe unfolds. This is similar to how space and time might be thought of as substrates, the fundamental fabric on which matter and energy exist. We do not yet know what space and time fundamentally are, but we know that they provide the arena in which physical processes occur. Dark matter may be similar. We do not yet know what dark matter fundamentally is, but we know that it provides the gravitational structure on which the visible universe is built. Understanding dark matter as cosmic scaffolding is therefore understanding the universe from the bottom up. It is recognizing that what we see, galaxies, stars, us, is built on a foundation of something invisible and largely mysterious. It is recognizing that we are not the substance of the universe. We are the details sketched on top of a much larger, mostly invisible structure. Imagine a perspective from far above the universe, infinitely far, looking down at the entire cosmos at once. From this perspective, the cosmic web is visible. You can see the filaments of dark matter concentration. You can see the nodes where filaments intersect. You can see the voids. Scattered along the filaments and clustered at the nodes are tiny luminous points, galaxies. Each galaxy contains billions of stars. Each star may contain planets. On some of those planets, life may exist, producing consciousness and intelligence. These conscious beings, these intelligent creatures, live on planets orbiting stars and galaxies concentrated along dark matter filaments. They look up at the sky. They see stars. They see galaxies. They begin to wonder what the universe is made of. They observe the motion of galaxies and realize that something is missing. They infer the existence of dark matter. Gradually, they begin to understand that they are not living in the substance of the universe. They are living in the details sketched on the cosmic scaffolding. This realization that we are decoration on a much larger framework is one of the most profound insights that conscious creatures can achieve. It is a realization of humility and perspective. It places us in context. It shows us where we actually stand in the grand structure of things. The universe was not always like this. At the beginning, there were no galaxies, no stars, no planets, no atoms, no structure at all. The early universe was almost perfectly uniform. It was hot and dense, it was expanding rapidly, but it was homogeneous, the same everywhere. Over 13.8 billion years, that uniformity has given way to complexity. Structures have emerged, galaxies have formed, the cosmic web has crystallized, stars have ignited, planets have coalesced, life has evolved. This is the story of how the universe transformed itself from near-perfect uniformity to the intricate, structured cosmos we observe today. It is a story of structure emerging from emptiness, of complexity arising from simplicity, of the universe organizing it. At the moment of the Big Bang, or as close to the beginning as we can meaningfully speak of, the universe was infinitely hot and infinitely dense. Space itself was being created. Time itself was beginning. In these first fractions of a second, the concept of structure was meaningless. There was no space large enough for structures to exist. There was no time enough for structures to develop. But almost immediately, within the first fraction of a second, the universe began to expand and cool. Space expanded. The density decreased. The temperature dropped. Within the first microsecond, fundamental particles formed. Quarks combined into protons and neutrons. The basic building blocks of matter began to exist. Within the first few minutes, these protons and neutrons combined into atomic nuclei. The first atomic nuclei formed: hydrogen, helium, and tiny amounts of lithium. But at this stage, the universe was still almost perfectly uniform. The density varied from place to place, but only by tiny amounts, 1 part in 100,000. The variations were so small that if you averaged over regions the size of 1 billion light years, the universe looked the same everywhere. There were no galaxies, no stars, no planets, no atoms even. The electrons were still separate from the nuclei, floating free in a soup of radiation. The universe was simple. It was uniform. It was featureless. For the first 380,000 years after the Big Bang, the universe was opaque. The universe was filled with a soup of charged particles: protons, electrons, photons. The photons could not travel far before colliding with charged particles. The universe was foggy. Light could not penetrate it. During this era, ordinary matter, atoms, could not form structures. The radiation pressure from photons was too intense. It pushed against any gathering of matter. Any region that began to clump together would be blown apart by radiation pressure. But dark matter, being invisible and non-interacting, was not affected by radiation pressure. Dark matter could respond freely to gravity. Even during this radiation-dominated era, dark matter was beginning to organize. Small density fluctuations in dark matter, fluctuations left over from the quantum uncertainty of the Big Bang, were being amplified by gravity. Regions of higher dark matter density were pulling in more dark matter. Regions of lower density were losing dark matter. The contrast was growing, but slowly. The universe's dark matter was beginning to organize into structures, but these structures were still tiny. They were just beginning to form. Meanwhile, ordinary matter was locked in place by radiation pressure. It could not fall into the dark matter wells. It could not form structures. It was passive, waiting. At about 380,000 years after the Big Bang, something crucial happened: recombination. The universe had cooled enough that electrons could combine with protons to form neutral hydrogen atoms. The universe transitioned from a plasma of charged particles to a gas of neutral atoms. This had an immediate consequence. Neutral atoms do not interact strongly with photons. Radiation could now travel freely through space. The universe became transparent. And here is the crucial point. With radiation pressure removed, ordinary matter was finally free to respond to gravity. But ordinary matter did not start from scratch. Dark matter had already been organizing for 380,000 years. Dark matter had already created gravitational wells. Ordinary matter began to fall into these pre-existing structures. This was the moment when ordinary matter could finally participate in structure formation. This was when the universe transitioned from dark matter-only structure formation to a universe where both dark matter and ordinary matter were organizing. The density fluctuations that would eventually become galaxies, galaxy clusters, and the cosmic web began to grow more rapidly after recombination. After recombination, the universe entered a period sometimes called the cosmic dark ages. No stars had formed yet. The universe was filled with neutral hydrogen gas, with dark matter clumped into structures, but no luminous objects. The universe was dark. But structure was developing rapidly. Ordinary matter was falling into dark matter wells. Gas was accumulating in the densest regions. The density contrast was growing. The growth of structure during this era followed a predictable pattern. Regions that were slightly denser than average pulled in more matter. They became denser still. Their gravity increased. This positive feedback loop amplified the initial small density fluctuations into larger and larger structures. By the end of the cosmic dark ages, after about 100 million years, the universe had developed clear structure. Filaments of dark matter and gas stretching across space nodes where filaments intersected, where dark matter and gas were highly concentrated. Voids between filaments, where dark matter and gas were much sparser. The cosmic web was taking shape, but it was still dark. No stars had ignited yet. The densest regions, the nodes, had accumulated so much gas that gravity was becoming intense. Temperatures were rising, but they had not yet reached the temperature needed to ignite hydrogen fusion. About 100 million years after the Big Bang, the first stars ignited. In the densest regions, the nodes of the cosmic web, gas had accumulated so thickly that gravity pulled it together into spheres. These spheres of gas collapsed under their own weight. As they collapsed, the gas became hotter and denser. Eventually, the temperature and pressure at the center of these collapsing gas spheres reached the point where hydrogen fusion could begin. The first stars were born. These first stars were different from modern stars. They were more massive. They were hotter. They burned their fuel much faster. They lived for only a few million years before exploding as supernovae. But they were the first light in the universe. After 100 million years of darkness, the universe began to glow. These first stars filled the space around them with ultraviolet radiation. This radiation ionized the neutral hydrogen gas, knocked the electrons off the hydrogen atoms, turning the gas back into a plasma. The universe began to reionize. The cosmic dark ages ended. Over the next several hundred million years, star formation accelerated. As the first stars exploded as supernovae, they created elements heavier than helium: carbon, nitrogen, oxygen, iron, silicon. The periodic table of elements began to build up in space. These elements were scattered back into the gas by the supernovae explosions. The gas became enriched with heavy elements. Subsequent generations of stars could form from this enriched gas. More stars formed, more galaxies assembled. The cosmic structure that had been forming invisibly in dark matter finally became visible as light. During this era, galaxies were smaller and less organized than modern galaxies. Many of them were irregular in shape. Many collided and merged with each other. The universe was chaotic. But over time, galaxies began to settle into larger structures. Galaxy clusters formed. The cosmic web became more defined. By about 1 billion years after the Big Bang, the universe looked recognizably like the universe we know today, though with important differences. Galaxies existed. Galaxy clusters existed. The cosmic web existed. Stars were shining throughout the universe, but the structures were younger. They were still developing. The universe was still in its youth. From about 1 billion years after the Big Bang to the present day, a span of about 12.8 billion years, cosmic structure has continued to grow and evolve. Galaxies have continued to form. Galaxy clusters have continued to assemble. The cosmic web has continued to become more pronounced. The process is slow. On human timescales, it is imperceptibly slow, but over billions of years, the changes are dramatic. Let us trace the evolution of a single structure, a galaxy cluster. In the early universe, a region of slightly elevated dark matter and gas density begins to accumulate more material. Galaxies begin to form within it. The cluster begins to assemble. Over the next few billion years, more galaxies form and fall into the cluster. More dark matter accumulates. Smaller clusters merge with the larger one, combining their populations of galaxies. The cluster becomes denser. It becomes more organized. Individual galaxies within the cluster collide and merge, creating larger galaxies. After 10 billion years, the cluster reaches a relatively stable state. It contains thousands of galaxies. It is gravitationally bound. It is no longer growing as rapidly, but it is still evolving. Individual galaxies within the cluster continue to interact. Mergers continue to occur, though more slowly. The most massive galaxies in the cluster continue to grow by merging with smaller neighbors. This process, structure formation and evolution through gravitational accumulation and merging, has been occurring throughout the universe for the past 13 billion years. The growth of cosmic structure follows a principle called hierarchical structure formation. Small structures form first. They accumulate into larger structures. Larger structures accumulate into even larger structures. Consider the hierarchical layers. Scale 1. Star clusters, light years. In the dense regions of galaxies, stars cluster together under gravity. These clusters contain hundreds or thousands of stars. Scale 2. Galaxies, thousands of light years. Billions of stars cluster together, held in place by dark matter halos. Galaxies are the next level up. Scale 3. Galaxy groups, millions of light years. A few galaxies cluster together gravitationally. The local group, which contains the Milky Way and Andromeda, is an example. Scale 4. Galaxy clusters, millions of light years. Hundreds or thousands of galaxies cluster together. Galaxy clusters are much larger than galaxy groups. Scale 5. Superclusters, hundreds of millions of light years. Multiple galaxy clusters cluster together into superclusters. The Virgo supercluster, which contains the local group, is an example. Scale 6. Filaments and the cosmic web, billions of light years. Superclusters and smaller structures are organized into filaments that stretch across billions of light years. The filaments form the cosmic web. Scale 7. The observable universe, billions of light years. All of these structures together make up the observable universe. Each level of the hierarchy formed after the smaller levels had already assembled. Stars formed first, galaxies formed next, galaxy clusters formed after that, superclusters in the cosmic web formed last. And this process is still ongoing. Structures at every level are still growing and evolving. Galaxies are still merging. Galaxy clusters are still assembling. The cosmic web is still becoming more pronounced. One of the primary mechanisms of structure growth is merging. Smaller structures collide and merge to create larger structures. A galaxy collision is a slow process. When two galaxies collide, they do not immediately crash together. Their dark matter halos interact gravitationally. The galaxies enter a spiral orbit, gradually approaching each other. Over hundreds of millions of years, the two galaxies slowly merge into one. During the merger, the stars from both galaxies are redistributed. The gas from both galaxies mixes and collides. New stars form from the colliding gas. The merger is a violent, chaotic event, but it is stretched over a billion-year timescale. After the merger is complete, the two galaxies have become one larger galaxy. The merger has created structure at a larger scale. Similarly, when two galaxy clusters collide, they merge over the course of billions of years. The dark matter from both clusters mixes. The galaxies from both clusters are redistributed. The merger creates a larger, more massive galaxy cluster. These mergers are not rare events. In the early universe, mergers were frequent. Galaxies were closer together. Structures were still forming. Collisions were common. As the universe has aged, mergers have become less frequent. Structures have become more separated. The universe has expanded. But mergers still occur today. The Milky Way and Andromeda are on a collision course and will merge in about 4.5 billion years. Mergers are a fundamental mechanism of structure growth. Through mergers, the universe has built larger and larger structures over billions of years. For the first 9 billion years or so after the Big Bang, the evolution of cosmic structure was dominated by gravity and dark matter. Dark matter accumulated, galaxies formed, galaxy clusters assembled, the cosmic web took shape. But about 4 billion years ago, which corresponds to about 9.8 billion years after the Big Bang, something changed. At this point in cosmic history, dark energy began to dominate the universe's expansion. Dark energy is a mysterious form of energy that permeates space and accelerates the expansion of space. Before dark energy became dominant, the expansion of the universe was slowing down due to gravity. Gravity was pulling structures together faster than expansion was pulling them apart. But dark energy works in the opposite direction. It accelerates the expansion of space. It pulls structures apart. Once dark energy became dominant, the rate of expansion began to accelerate. The universe began to expand faster and faster. This had profound consequences for structure formation. On very large scales, between galaxy clusters, between filaments, expansion began to win. Structures began to be pulled apart by expansion faster than gravity could pull them together. But on smaller scales, within galaxy clusters, within galaxies, gravity was still strong enough to overcome expansion. These structures continued to grow. The consequence is that structure formation has been slowing down in recent billions of years. The universe is still developing structure, but more slowly than it was earlier. In the future, if dark energy continues to dominate, structure formation may eventually stop altogether. Galaxy clusters may become increasingly isolated. The cosmic web may begin to tear apart. But this is far in the future. For now, the cosmic web remains intact and continues to evolve. Individual galaxies have evolved dramatically over cosmic time. In the early universe, galaxies were small and irregular. They were chaotic. They were actively forming stars at high rates. As the universe aged, galaxies evolved. Small galaxies merged to form larger galaxies. Irregular galaxies became more organized into spiral and elliptical shapes. Galaxy mergers play a crucial role in galactic evolution. Each merger creates a larger galaxy. Each merger redistributes the stars and gas. Each merger can trigger intense bursts of star formation. The largest galaxies we observe today are the products of many mergers. They have grown by consuming smaller neighbors over billions of years. The Milky Way is a good example. The Milky Way today is a spiral galaxy with about 200 to 400 billion stars. But it has not always been this large. In the early universe, what would become the Milky Way was much smaller. Over billions of years, it has grown through the absorption of smaller satellite galaxies. It has collided and merged with other galaxies. The Andromeda Galaxy, our nearest large galactic neighbor, has a similar history. It too has grown through mergers and consumption of smaller galaxies. In 4.5 billion years, the Milky Way and Andromeda will collide. They will enter a long, slow merger that will take about 2 billion years to complete. The result will be a single larger galaxy, sometime called Milkomeda or Milkdromeda. This merger is the future. It will produce a new, larger structure. It will continue the process of structure growth through merging. As structure has evolved, the chemical composition of the universe has also evolved. In the beginning, the universe contained only the lightest elements, hydrogen, helium, and trace amounts of lithium. These elements were created in the Big Bang and in the early universe. But as stars formed, they created heavier elements through nuclear fusion. Carbon, nitrogen, oxygen, silicon, iron, the periodic table of elements was being built inside stars. When massive stars died as supernovae, they scattered these heavy elements back into space. The gas was enriched. The next generation of stars formed from this enriched gas. They contained more heavy elements. Over billions of years, the chemical composition of the universe has become richer. More and more elements have been created. The abundance of heavy elements has increased. This has profound implications for structure formation. Early galaxies, made mostly of hydrogen and helium, formed differently than modern galaxies, which contain significant amounts of carbon, nitrogen, oxygen, and other heavy elements. The evolution of galactic structure and the chemical evolution of the universe are deeply intertwined. As the universe has evolved chemically, the nature of structures has changed, and the existence of heavy elements has enabled the formation of rocky planets and the emergence of life. Without billions of years of stellar alchemy, converting hydrogen and helium into heavier elements, the Earth would not exist. We would not exist. Embedded within the story of galactic and cosmic structure formation is the story of planetary system formation. Planetary systems form in the disks of gas and dust that surround newborn stars. In the early universe, the first stars formed from gas containing almost no heavy elements. These first stars were massive. They lived briefly. They exploded as supernovae. They died without forming planetary systems. But as the universe evolved, stars formed from increasingly enriched gas. Stars that formed a few 100 million years after the Big Bang could, for the first time, form planetary systems with rocky planets. As the universe continued to age, more and more stars formed planetary systems. The techniques and mechanisms of planetary formation were refined through trial and error. Different types of planetary systems emerged. By the time the Sun formed, about 4.6 billion years ago, the universe was 9.2 billion years old. The Sun formed from gas enriched with billions of years of stellar alchemy. The Sun's planetary system, including the Earth, formed from the disk of gas and dust surrounding the young Sun. This planetary system is the product of cosmic structure formation at the smallest scales. It is part of a galaxy, which is part of a galactic group, which is part of a galaxy cluster, which is part of the cosmic web. The Earth is a structure that could only exist because larger structures had already formed. Without galaxies, there would be no stars. Without stars, there would be no rocky planets. Without rocky planets, there would be no Earth. Without the Earth, we would not exist. Embedded within the story of planetary system formation is the story of life. Life emerged on Earth about 3.8 to 4 billion years ago, about 700 million to 1.2 billion years after the Earth itself formed. Life did not emerge by chance. It emerged because the conditions on Earth made it possible. A rocky planet in the habitable zone of a star with liquid water, with a protective atmosphere, with complex chemistry. These conditions allowed life to emerge. Life is a structure. It is a highly organized structure. Life organizes matter into increasingly complex patterns. Cells, organisms, ecosystems, biospheres. Each level represents a new scale of organization. Life could only emerge after billions of years of cosmic structure formation. Life depends on planetary systems. Planetary systems depend on stars. Stars depend on galaxies. Galaxies depend on the cosmic web. The cosmic web depends on dark matter. Life is embedded in this hierarchy. Life is a structure within structures, nested within ever larger structures. And from life, consciousness emerged. Consciousness is the ultimate expression of structure formation. It is the universe organizing itself in such a way that it can observe and understand itself. Humans are structures. We are collections of atoms organized into molecules, organized into cells, organized into tissues, organized into organs, organized into organisms. We are also structures within structures. We are products of planetary formation, stellar formation, galactic formation, cosmic web formation. When we look up at the night sky and observe the stars and galaxies, we are part of the universe observing itself. We live 13.8 billion years after the Big Bang. The universe at this moment contains billions of galaxies, trillions of stars, countless planets, complex chemical elements, structures at every scale from atoms to galaxy clusters. Life in at least one location, Earth as far as we know. Consciousness in at least one location, humans as far as we know. The cosmic web stretches across billions of light years. Filaments of galaxies connect nodes of galaxy clusters. Voids stretch between filaments. All of this structure is underlaid by dark matter. Galaxies are still forming. Galaxies are still merging. The cosmic web is still evolving. Stars are still being born and dying. Planets are still forming. Life is still evolving. The universe is not static. It is dynamic. It is still developing. It is still becoming. We are living in the middle of a process. We have not reached the end. We are not living in the final state of the universe. What will the universe look like in the future? In 1 billion years, the Milky Way and Andromeda will be in the middle of their merger. The combined galaxy will be restructuring itself. New stars will be forming. The remnants of the two galaxies will be reorganizing into a single, larger system. In 4 billion years, the Milky Way and Andromeda will have mostly merged. The combined galaxy will be settling into its final form. It will be larger and more massive than either parent galaxy. In 10 billion years, the universe will be 23.8 billion years old. The sun will have long since died. The Earth will have been consumed by the sun's expansion and death. But other stars will still be shining. Other galaxies will still be forming. The universe will still be creating structure. In 100 billion years, the universe will be 113.8 billion years old. Most of the stars that are currently shining will have died, but new stars will have formed from the remains of old stars. Galaxy clusters will be more isolated as dark energy accelerates the expansion of space. The cosmic web will be stretched thinner. The structures that exist today will be increasingly separated. In 1 trillion years, the universe will be over 1 trillion years old. the universe will be vastly older than it is today. Mergers will have largely stopped. Galaxy clusters will be isolated islands separated by vast empty spaces. The cosmic web, as we know it, may have largely been torn apart by dark energy, but structures will still exist. Galaxy clusters will still contain galaxies. Galaxies will still contain stars. However, by this point, most stars will have burned out. The universe will be much darker than it is today. In 10 to the power of 100 years, 1 Google years. The universe will be inconceivably old. Most stars will have long since died. Black holes will be the only remaining massive objects, slowly evaporating through Hawking radiation. The universe will be approaching a cold, dark, empty state. In the infinitely distant future, if the universe expands forever, it will eventually reach a state of almost complete emptiness. Protons may decay. All structure may dissolve. The universe will approach maximum entropy, complete disorder. But this is far, far in the future. For the next trillions of years, the universe will still contain structure. It will still be evolving. Over the course of cosmic history, the rate of structure formation has changed. In the very early universe, right after recombination, the rate of structure growth was rapid. Tiny density fluctuations were being amplified by gravity. The contrast between dense and sparse regions was increasing exponentially. As time went on, this exponential growth slowed. Structures reached larger and larger sizes, but the rate of growth declined. By about 1 billion years after the Big Bang, the fastest period of structure growth was over. The cosmic web was largely in place. Most galaxies had formed. From 1 billion years to about 9 billion years after the Big Bang, structure continued to grow, but more slowly. Galaxies continued to merge. Galaxy clusters continued to assemble. But the rate of new structure formation slowed. About 4 billion years ago, when dark energy became dominant, the rate of structure formation slowed even more dramatically. Structure still forms, but the expansion of space is now competing against gravity on large scales. In the very distant future, structure formation may essentially stop. The universe will be so expanded, so dilute, that new structures will not form. Existing structures will slowly be torn apart. The evolution of cosmic structure gives us a window into the arrow of time. The universe began in a state of near-perfect uniformity. It was simple, it was homogeneous, it was featureless. Over time, structure has emerged. The universe has become more complex. It has developed galaxies, stars, planets, life, consciousness. This progression from simplicity to complexity is the arrow of time. It is an increase in complexity. It is an increase in the number of distinct structures. It is an increase in organization. The second law of thermodynamics says that entropy, disorder, always increases. But this seems contradictory. We observe the universe becoming more structured, more organized, not less. The resolution is that while entropy does increase globally, local regions can decrease in entropy if energy is being added. The early universe was a high-energy environment. Structure could form at the expense of increasing overall entropy. Over billions of years, the universe has converted the energy of its initial expansion into structure. This structure takes the form of galaxies, stars, planets, and life. The formation of structure over time is the visible manifestation of the second law of thermodynamics. The universe is becoming more disordered overall, but this disorder is being concentrated into the expansion of space while structure emerges in the contracting regions. As structure has evolved, the information content of the universe has increased. In the beginning, the universe contained very little information. It was nearly uniform. If you described the early universe, you would need very little information. You would just say, it was hot, dense, and uniform everywhere. But the present-day universe contains vast amounts of information. You need an enormous amount of information to describe all of the galaxies, stars, planets, and other structures that exist today. Information has been created over cosmic time. This information is encoded in the structure of the universe. Some of this information is encoded in the positions and velocities of galaxies. Some is encoded in the internal structure of galaxies, the distribution of stars and dark matter. Some is encoded in the stars themselves, their masses, compositions, ages. Some is encoded in planets. Some is encoded in life. Some is encoded in human consciousness and knowledge. In a sense, the universe has been writing its own story over billions of years. The story is written in the language of structure. The information is encoded in the shapes and distributions of matter and energy. We humans are part of this process. Our consciousness, our knowledge, our understanding of the universe. These are also forms of information creation. We are the universe becoming aware of itself, developing the ability to understand its own structure. Looking at the history of the universe, one conclusion stands out. Structure is the fundamental feature of the universe. The universe did not remain uniform. It could not remain uniform. The tiny quantum fluctuations in the early universe were amplified by gravity into larger and larger structures. Structure formation is not a secondary feature. It is not something that happens in addition to the main story. Structure formation is the main story. The universe's primary activity over billions of years has been to organize itself, to take near uniformity and transform it into complexity, to create galaxies, stars, planets, life. This is not accidental. It is a natural consequence of the laws of physics. Given an expanding universe that begins in near uniformity, structure formation is inevitable. The universe organizes itself. This is what the universe does. As we have traced the evolution of cosmic structure, one pattern emerges repeatedly. Structures at different scales are deeply connected. They are not independent. They form a nested hierarchy. Stars form within galaxies. Galaxies form within galaxy clusters. Galaxy clusters form filaments. Filaments make up the cosmic web. But the connection goes deeper. The properties of larger structures determine the conditions for smaller structures to form. The cosmic web determines where galaxy clusters can form. Galaxy clusters determine where galaxies can form. Galaxies determine where stars can form. Going the other way, smaller structures build larger ones. Stars cluster into galaxies. Galaxies cluster into galaxy clusters. Galaxy clusters organize into filaments and the cosmic web. This nested hierarchical structure is not unique to cosmology. It appears everywhere in nature. Atoms form molecules. Molecules form cells. Cells form organisms. Organisms form ecosystems. Ecosystems form biospheres. At every scale, smaller units combine to form larger wholes. Each whole has properties that emerge from its parts, but cannot be predicted from the parts alone. This is the principle of emergence, and emergence is the fundamental organizing principle of the universe. The evolution of cosmic structure has directly enabled the emergence of life. For life to exist, you need heavy elements. Life requires carbon, nitrogen, oxygen, phosphorus, and other heavy elements. These did not exist in the Big Bang. They had to be created in stars and scattered by supernovae. This required billions of years of stellar evolution. Planets. Life requires a place to live. Planets are structures that form around stars. Planetary system formation requires the right conditions. It requires enriched gas, stellar stability, and the right orbital dynamics. These conditions only became common billions of years after the Big Bang. Liquid water. Life as we know it requires liquid water. This requires a planet in the habitable zone of a star with the right composition and the right atmosphere. This is an incredibly specific condition. Stability. Life requires a stable environment to evolve in. A star must be stable for billions of years. A planet's climate must be relatively stable. The orbits in a planetary system must remain stable. Again, this requires the right initial conditions and billions of years of evolution. All of these conditions are products of cosmic structure formation. Life is not an accident that happened to occur in the universe. Life is a natural consequence of cosmic structure evolution. Here is a profound observation. The universe is a self-organizing system. It began in near uniformity. Through the working of gravity and the expansion of space, it organized itself into structure. No external agent organized the universe. No designer arranged the galaxies. No creator positioned the stars. The universe organized itself. The laws of physics were sufficient. Gravity, expansion, and quantum mechanics working together were sufficient to organize near uniformity into the complex structure we observe today. This is not to say the universe is alive or conscious or intentional. It is not. It is simply following the laws of physics. But the laws of physics, operating over billions of years, naturally produce organization. Structure emerges spontaneously. Complexity arises from simplicity. This principle of self-organization is profound. It means that order can arise naturally from chaos. It means that complexity is not improbable. It is a natural consequence of time and physics. And if self-organization is natural at cosmic scales, why not at smaller scales? Why shouldn't self-organization also occur in chemistry, in biology, in ecology, in human societies? The universe self-organizes at all scales. This is its fundamental nature. There is an apparent paradox in the universe's evolution. The second law of thermodynamics says that entropy, disorder, always increases. But we observe the universe becoming more structured, more organized, not less. How can this be? The resolution is subtle but important. The second law of thermodynamics applies to the universe as a whole. The total entropy of the universe is indeed increasing. The universe is moving toward a state of maximum disorder. But this does not prevent local regions of the universe from becoming more ordered. Energy can flow from one place to another. If energy is extracted from one region and dissipated in another, the first region can become more ordered, while the second becomes more disordered. This is exactly what has happened in the universe. The early universe was a high-energy environment. This energy was distributed relatively uniformly. In a sense, the early universe was at maximum entropy for the conditions it was in. It was uniform and disordered. Over billions of years, gravity has pulled matter together into structures. Stars, galaxies, and galaxy clusters are highly ordered systems. They are low-entropy configurations of matter. How is this possible if entropy must increase? The answer is that the energy that has gone into organizing matter into structures has been radiated away as light and heat. This light and heat have been dispersed throughout the universe, increasing the entropy of the radiation field. The net effect is that total entropy has increased, as required by the second law. But locally, in the regions where matter has clustered, entropy has decreased. Highly organized structures have emerged. The universe pays for the creation of structure by increasing entropy elsewhere. In a sense, the universe is trading dispersed energy for organized matter. Looking at the evolution of cosmic structure gives us a perspective on our place in the universe. We are structures. Our bodies are organized matter. Our minds are organized information processing systems. Our societies and civilizations are organized social structures. We are products of cosmic structure formation. We are made of atoms created in stars. We live on a planet formed around a star in a galaxy. That galaxy is part of a galaxy cluster. That cluster is part of the cosmic web. When we understand cosmic structure evolution, we understand our own origins. We understand that we are not separate from the universe. We are expressions of it. We are how the universe has organized itself. We are the universe becoming aware of itself. We are how the universe observes itself and understands itself. This realization has profound implications. It means that studying the universe is, in a sense, the universe studying itself. It means that our consciousness and knowledge are part of the same process that created galaxies and stars. It means that we are not outside observers of the universe. We are part of it. We are expressions of it. The evolution of cosmic structure is not finished. We live 13.8 billion years after the Big Bang. The universe is middle-aged, if you like. It still has trillions of years ahead of it. In the coming billions of years, the Milky Way and Andromeda will merge. New stars will form. Other galaxies will collide and merge. The cosmic web will continue to evolve. In the coming trillions of years, stars will burn out. Black holes will evaporate. The universe will become colder and darker. But the principle remains the same. The universe will continue to organize itself. New structures may emerge that we cannot predict. The universe may surprise us. Or perhaps billions of years from now, if consciousness and intelligence emerge elsewhere in the universe, they may also observe the cosmic structure and attempt to understand it. They will discover the same laws of physics. They will trace the same history. They will come to the same conclusions. The structure of the universe is real. It is not dependent on human observation. It would exist whether or not we were here to observe it. But the fact that we are here, that conscious creatures have emerged who can observe and understand cosmic structure, is itself a remarkable product of structure formation. The universe is not random. If you measure a galaxy's brightness, you can predict how fast it rotates. If you measure a galaxy's mass, you can predict the mass of the black hole at its center. If you know the size of a galaxy cluster, you can estimate how long it has been assembling. The universe follows hidden rules. Disparate properties are connected by invisible threads. Things that seem unrelated turn out to be intimately linked. These connections are not obvious. They are not intuitive. They are counterintuitive. They suggest that the universe is more deeply organized than we initially suspect. This is the story of those hidden relationships, the correlations that reveal the universe's secret structure. In 1977, two astronomers named Brent Tully and Richard Fisher noticed something strange. They were studying spiral galaxies and measuring two properties: luminosity, how bright the galaxy is, how much light it emits; rotation velocity, how fast the galaxy's disk rotates. Intuitively, these should be unrelated. Why would brightness correlate with rotational speed? They measure completely different things. But Tully and Fisher discovered that they are related. In fact, they are related by a precise mathematical law. A galaxy's luminosity is proportional to the fourth power of its rotation velocity. This means a galaxy that rotates twice as fast is 16 times brighter. 2 to the power of 4 equals 16. A galaxy that rotates 3 times as fast is 81 times brighter. 3 to the power of 4 equals 81. This relationship is called the Tully-Fisher relation. It is so precise that if you measure a galaxy's rotation velocity, you can predict its brightness with remarkable accuracy. And if you measure its brightness, you can predict its rotation velocity. Why is this counterintuitive? At first glance, there is no obvious reason why rotational speed should predict brightness. These are measuring different properties. Rotation velocity depends on the galaxy's gravitational field and its mass distribution. Luminosity depends on how many stars the galaxy contains and how luminous those stars are, yet they are connected by a precise mathematical relationship. Why does this relationship exist? The Tully-Fisher relation exists because of a deep connection between a galaxy's mass and its luminosity. More massive galaxies rotate faster. This is because faster rotation is needed to balance the stronger gravitational pull of more massive galaxies. More massive galaxies also tend to contain more stars, and more stars means more light. So both rotation velocity and luminosity are consequences of galaxy mass. They both increase with mass, and they happen to increase in a way that produces a precise mathematical relationship. The Tully-Fisher relation is a window into the fundamental properties of galaxies. It tells us that galaxies of different sizes follow the same rules. There is a universal relationship connecting their properties. Practical applications. The Tully-Fisher relation has practical importance. Galaxies are far away. It is difficult to measure their distance directly, but if you can measure a galaxy's rotation velocity using the Doppler shift of its light, you can use the Tully-Fisher relation to predict its brightness. And if you know its actual brightness by measuring the light we receive, you can calculate how far away it must be. The distance calculation works like this. Measure the galaxy's rotation velocity, then predict its intrinsic brightness. Measure the apparent brightness, how bright it appears from Earth, then compare to intrinsic brightness. The difference tells you the distance. Using this method, astronomers have mapped the distances to thousands of distant galaxies. The Tully-Fisher relation transforms a measurement of motion, rotation, into a measurement of distance. It is a cosmic ruler. In the 1990s and 2000s, astronomers made a remarkable discovery. Every large galaxy contains a supermassive black hole at its center. This was surprising enough, but then they made an even more surprising discovery. The mass of a galaxy's central black hole is correlated with properties of the galaxy itself. Specifically, the black hole mass correlates with the velocity dispersion of stars in the galaxy's bulge. Velocity dispersion is a measure of how fast stars are moving in random directions as opposed to organized rotation. This relationship is called the m-sigma relation. Black hole mass approximately equals 150 times velocity dispersion to the power of 5. The exact coefficient varies slightly depending on which studies you look at, but the relationship is robust. This means a galaxy bulge with a velocity dispersion of 100 kilometers per second has a central black hole of roughly 100 million solar masses. A galaxy bulge with a velocity dispersion of 200 kilometers per second has a central black hole of roughly 3.2 billion solar masses. 2 to the power of 5 equals 32 times larger. Why is this counterintuitive? This is profoundly counterintuitive. The central black hole is tiny. It occupies a region smaller than our solar system. It contains less than 1% of the galaxy's total mass. The galaxy bulge is enormous. It contains billions of stars. It extends for tens of thousands of light years. Yet the black hole mass is correlated with the galaxy bulge properties. The black hole somehow knows about the galaxy surrounding it. The galaxy somehow knows about the black hole at its center. How can such a tiny object be correlated with such a massive structure? Why does this relationship exist? The m-sigma relation suggests that black holes and galaxy bulges co-evolve. They grow together. The mechanism is thought to be this. Early in a galaxy's life, gas falls toward the center and feeds the black hole. The black hole grows. As the black hole grows, it becomes more powerful. Eventually, it becomes so powerful that it ejects material outward in jets and winds. These jets and winds are so energetic that they blow gas out of the galaxy. They heat the surrounding gas. This is called AGN feedback. AGN equals active galactic nucleus. The feedback stops star formation and heats the galaxy bulge. The velocity dispersion of the bulge increases. An equilibrium is reached where the black hole is large enough that its feedback prevents further growth of the galaxy. At this point, black hole mass and bulge properties are balanced, so the M-sigma relation exists. Because black holes and galaxies regulate each other's growth, they are in a dynamic equilibrium. The M-sigma relation reveals this connection. It shows that despite their vast difference in size, black holes and galaxies are intimately linked. Practical implications. The M-sigma relation allows astronomers to estimate black hole masses in distant galaxies without directly observing the black hole. If you can measure the velocity dispersion of stars in a galaxy's bulge by analyzing the Doppler shifts of their light, you can estimate the black hole mass. This has revealed that supermassive black holes are ubiquitous. Nearly every large galaxy has one. Here is a counterintuitive fact. Two galaxies with the same mass, age, and composition can look completely different if they are in different environments. Galaxies and galaxy clusters look different from isolated galaxies. The effect of environment on galaxy properties. Isolated galaxies, galaxies far from other galaxies, are often spiral galaxies, have organized disk structures, have active star formation, new stars are being born, contain gas, fuel for future star formation. Galaxies in clusters, galaxies in dense groups with many neighbors, are often elliptical galaxies, have smooth, featureless structure, have little or no star formation, few new stars being born, are gas poor, most gas has been removed. This is counterintuitive because the galaxies themselves haven't changed. Same mass, same age, same fundamental properties. But their appearance and behavior are dramatically different based on where they are. Mechanisms causing environmental effects. Several mechanisms explain why environment affects galaxies. 1. Ram pressure stripping. As a galaxy falls into a cluster, it passes through the hot gas that fills the cluster. This creates a wind that strips away the galaxy's own gas. The gas is blown off the galaxy, leaving it gas poor. Without gas, star formation stops. The galaxy becomes quiescent. 2. Tidal effects. Passing near other galaxies creates tidal forces. These forces can distort a galaxy's shape, trigger star formation, or even pull off streams of stars. 3. Galaxy mergers. In dense clusters, galaxy encounters are common. Two galaxies can collide and merge, creating a larger galaxy. The merger is violent and triggers intense star formation, followed by quenching, the stopping of star formation, as the merger completes. 4. Gravitational heating. Frequent encounters with other galaxies heat up the system dynamically. Gas is heated to high temperatures where it cannot form stars. The result, a correlation between environment and galaxy properties. Galaxy clusters are dominated by elliptical quiescent galaxies. The group environment produces this result. Isolated regions contain more spiral star-forming galaxies. This means a galaxy's appearance and properties depend not just on what it is, but on where it is. This is a profound correlation. Position predicts properties. Dark matter halos have a property called concentration. Concentration measures how centrally concentrated the dark matter is. A high concentration halo has dark matter clumped densely near the center. A low concentration halo has dark matter more spread out. In the 1990s, cosmological simulations revealed a surprising correlation. A dark matter halo's concentration is related to when it assembled. Specifically, halos that assembled early in the early universe have high concentration. Halos that assembled late, more recently, have low concentration. This is called the concentration mass relation or concentration assembly relation. The concentration of a halo depends on its internal structure, how the dark matter is distributed. This is a property of the halo itself. The assembly history is when the halo formed and grew. This is a property of the halo's past. Why should the internal structure be correlated with the past history? Why does this relationship exist? The reason is subtle and has to do with how dark matter halos grow. Dark matter halos grow by two mechanisms. One, smooth accretion. Dark matter from the surroundings slowly falls into the halo, adding to its mass. Two, mergers. Smaller halos collide and merge with the main halo, combining their masses. A halo that assembled early grew primarily by smooth accretion. The dark matter was added gradually to the growing halo. The halo had time to become concentrated and relaxed. A halo that assembled late grew by a combination of smooth accretion and major mergers. The mergers were violent and disrupted the internal structure. The halo did not have time to become as concentrated. So the concentration mass relation is a fossil record. It preserves information about how a halo assembled. This relationship, discovered in simulations, has been verified through observations. Astronomers measure the concentration of galaxy clusters using gravitational lensing. They compare the concentration to the age of the cluster, estimated from the properties of the galaxies it contains. The correlation holds. Older clusters are more concentrated than younger clusters. Implications. The concentration mass relation reveals that galaxy clusters and dark matter halos are not static objects. They are dynamic systems with histories. Their current structure reflects their past assembly. This is a profound correlation. Structure now predicts history then. Here is an important empirical finding. The universe is not filled with equal numbers of galaxies of all sizes. Instead, there's a specific distribution. Most galaxies are dwarf galaxies, small, faint, with relatively few stars. Dwarf galaxies are very numerous. Large, bright galaxies like the Milky Way are much rarer. This distribution is called the galaxy luminosity function. It describes how many galaxies of each brightness exist in a given volume of space. The galaxy luminosity function has a specific mathematical form. It can be described by a function called the Schechter function with specific parameters. The number of galaxies of a given luminosity decreases steeply for bright galaxies. In other words, there are many faint galaxies and few bright galaxies. Why is this counterintuitive? You might expect that galaxies would be distributed randomly across a range of sizes. You might expect a roughly uniform distribution or a bell curve. Instead, the distribution is strongly skewed towards small galaxies. The abundance drops off steeply for large galaxies. This is counterintuitive because it suggests that large galaxies are rare and special. The default mode of the universe is to make small galaxies, not large ones. Why does this distribution exist? The galaxy luminosity function reflects the way galaxies form and merge. Galaxies form in dark matter halos. The number of halos of different masses follows a specific distribution, derived from the properties of density fluctuations in the early universe. More dark matter halos are small than large. There are many more small halos than large ones. Small halos host dwarf galaxies. Large halos host large galaxies. So the abundance of galaxies reflects the abundance of dark matter halos. But the galaxy luminosity function is not exactly the same as the dark matter halo mass function. There are additional effects. Star formation efficiency varies with halo mass. In small halos, star formation is inefficient. Much of the gas is not converted to stars. In large halos, star formation is also less efficient due to feedback from supermassive black holes. There's a sweet spot at intermediate masses where star formation is most efficient. Mergers affect the luminosity function. When galaxies merge, they combine into a single larger galaxy. This removes galaxies from the faint end and adds to the bright end. Despite these complications, the overall trend remains. Dwarf galaxies are abundant, large galaxies are rare. Observational verification. The galaxy luminosity function has been measured precisely using deep surveys like the Sloan Digital Sky Survey, SDSS. The measurements confirm the Schechter function form. The galaxy luminosity function is one of the most robust measurements in cosmology. It is the same in galaxies observed billions of light years away, suggesting that the physical processes producing this distribution are universal. Implications. The galaxy luminosity function tells us something profound. The universe is dominated by small things, not large things. This applies not just to galaxies, but to dark matter halos, to galaxy clusters, to everything. The universe's default product is the small structure. Large structures are rare and form through the accumulation and merger of smaller structures. Galaxy clusters are held together by gravity. But how do you know they are in equilibrium, that they are not currently collapsing or expanding dramatically? One way to determine this is through the virial theorem. The virial theorem is a fundamental principle in physics. It relates the kinetic energy of a system, energy of motion, to its potential energy, gravitational binding energy. For a gravitationally bound system in equilibrium, 2 times kinetic energy equals minus potential energy. In a galaxy cluster, the kinetic energy comes from the random motions of galaxies. The potential energy comes from gravity. By measuring the velocities of galaxies in a cluster using redshift measurements, you can calculate the kinetic energy. Using the virial theorem, you can then infer the total gravitational binding energy. From the gravitational binding energy, you can calculate the total mass of the cluster. This is how astronomers measure the masses of galaxy clusters. The counterintuitive finding. Here is the counterintuitive part. When you measure galaxy masses and gas masses in a cluster, they add up to only about 15% of the mass required by the virial theorem. The remaining 85% is dark matter. This means, to keep a galaxy cluster in equilibrium, you need far more mass than you can see. The visible matter, galaxies and gas, is insufficient to gravitationally bind the cluster. Dark matter is essential. Without dark matter, galaxy clusters would not hold together. Galaxies would escape. The cluster would disperse. The virial relation reveals the hidden structure holding clusters together. Practical applications. The virial relation is used to measure dark matter in clusters. By measuring galaxy velocities, you can calculate the total mass, visible plus dark. Subtracting the visible mass gives you the dark matter mass. The virial relation is one of the most direct ways to weigh dark matter. Dark matter is not uniformly distributed. It is concentrated more densely in some places than others. In particular, dark matter halos have a specific radial density profile. The density is higher near the center and decreases with distance from the center. In the 1990s, N-body simulations, computer simulations of how gravity affects particles, revealed that dark matter halos have a universal density profile. This profile is called the NFW profile, after Navarro, Frank, and White, who first described it. The NFW profile has this form. Density is proportional to 1 over r times 1 plus r over rs squared, where r is the distance from the center and rs is a characteristic radius. This profile predicts that dark matter density decreases smoothly toward the center, following a specific mathematical form. The concentration paradox. Here is the counterintuitive finding. Simulations predict that dark matter should be concentrated near the centers of galaxies and galaxy clusters. The density should drop sharply toward the center. But observations of galaxy rotation curves and gravitational lensing suggest that dark matter density is less concentrated than simulations predict. Observations suggest dark matter halos have core-like density profiles, relatively flat density in the center. But simulations predict cuspy profiles, density that rises steeply toward the center. This is the core cusp problem. Why is this counterintuitive? The simulations are based on well-established physics, gravity, and dark matter interactions. The simulations should work, yet they predict something different from what we observe. This suggests that either the simulations are wrong, perhaps we don't understand dark matter or gravity as well as we think. The observations are wrong, perhaps our measurements have systematic errors. There is physics we don't understand. Perhaps dark matter interacts in ways we haven't accounted for. Small-scale physics affects large-scale structure. Perhaps processes like supernova feedback or black hole jets push dark matter around, altering its distribution. The core cusp problem remains unresolved. It is one of the most important puzzles in dark matter research. The correlation it reveals. The paradox reveals a deep correlation. The distribution of dark matter depends on feedback processes in galaxies. Small-scale physics, supernovae, black holes, affects large-scale structure, dark matter halos. Processes at different scales are connected. You cannot understand the distribution of dark matter without understanding stellar and black hole feedback. Just as the Tully-Fisher relation connects rotation velocity to brightness in spiral galaxies, there is a relation connecting galaxy mass to brightness in elliptical galaxies. This relation is called the Faber-Jackson relation. Luminosity is proportional to velocity dispersion to the power of 4. Velocity dispersion, recall, is a measure of how fast stars are moving randomly in the galaxy. This means a galaxy with a velocity dispersion of 100 kilometers per second is about 16 times brighter than a galaxy with a velocity dispersion of 50 kilometers per second. 2 to the power of 4 equals 16. The Faber-Jackson relation is remarkably tight. If you measure a galaxy's velocity dispersion, you can predict its brightness with good accuracy. Why is this counterintuitive? The Faber-Jackson relation reveals that elliptical galaxies, despite appearing simple and uniform, follow a precise mathematical relationship between their kinematics, motion, and their luminosity, brightness. Like the Tully-Fisher relation, it suggests that galaxies are not random collections of stars. They follow universal laws. Why does this relationship exist? The Faber-Jackson relation, like the Tully-Fisher relation, exists because both velocity dispersion and luminosity are consequences of galaxy mass. More massive galaxies have higher velocity dispersions. They are held together by stronger gravity. More massive galaxies also contain more stars, making them brighter. So both properties correlate with mass, producing the relationship. The Faber-Jackson's relation works for elliptical galaxies just as the Tully-Fisher relation works for spiral galaxies. Both are cosmic distance indicators. The Tully-Fisher and Faber-Jackson relations are powerful, but they work for specific galaxy types, spirals and ellipticals. In the 1980s, astronomers discovered an even more powerful relation that works for all types of galaxies. This relation is called the fundamental plane. The fundamental plane is a three-dimensional relationship connecting three galaxy properties: luminosity, L, how bright the galaxy is; velocity dispersion, sigma, how fast stars are moving randomly; effective radius, RE, the size of the galaxy. The relationship has the form: luminosity is proportional to velocity dispersion to the power of a times effective radius to the power of b, where AI is approximately 1.2 to 1.4 and b approximately 0.8 to 0.9. This means that if you know any two of these properties, you can predict the third with remarkable accuracy. Why is this counterintuitive? The fundamental plane unifies galaxies of different types under a single mathematical relationship. It suggests that despite galaxies' apparent diversity, they are governed by universal laws. The plane works for giant elliptical galaxies and tiny dwarf galaxies, for spiral galaxies and lenticular galaxies. This universality is counterintuitive. You would expect different galaxy types to have different relationships. The fundamental plane exists because all galaxies are held in equilibrium by gravity. The balance between kinetic energy, motion, and gravitational potential energy determines galaxy properties. More specifically, galaxies satisfy the virial theorem. Kinetic energy approximately equals gravitational potential energy. The kinetic energy is related to velocity dispersion. The gravitational potential energy is related to mass, which depends on luminosity and radius. So the virial theorem predicts a relationship between velocity dispersion, luminosity, and size. The fundamental plane is the observational manifestation of the virial theorem applied to galaxies. Practical implications. The fundamental plane is one of the most useful tools in observational astronomy. If you can measure any two galaxy properties, you can infer the third. This is especially useful for distance measurements. By measuring velocity dispersion and size, both of which can be determined from spectroscopy and imaging, you can infer luminosity. Comparing inferred luminosity to observed brightness gives distance. This method works for distant galaxies where other distance indicators fail. Here is a subtle but important correlation. The number of galaxy clusters changes with cosmic time. Early in the universe, several billion years after the Big Bang, there were fewer massive galaxy clusters. As the universe aged, the number of massive galaxy clusters increased. But this trend started to reverse relatively recently. In the recent universe, the last few billion years, the number of massive galaxy clusters has remained relatively constant or even decreased slightly. This evolution in cluster abundance reveals something profound. Dark energy has begun to affect cosmic structure. The correlation it reveals: the abundance of galaxy clusters at different redshifts, different cosmic epochs, is correlated with the expansion history of the universe. In the early universe, gravity was stronger than dark energy, so structures like clusters could form efficiently. As the universe aged, dark energy became increasingly important. Its repulsive effect slowed structure formation. By measuring how the abundance of clusters changes with cosmic time, astronomers can infer the properties of dark energy. This is called cluster abundance cosmology. It is one of the most powerful ways to constrain the nature of dark energy. The correlation is subtle but profound. The number of galaxy clusters now tells us about the universe's fate. Dark matter halos are not smooth. They contain substructure. Cosmological simulations predict that dark matter halos should contain numerous smaller dark matter clumps embedded within them. A Milky Way-sized halo should contain thousands or even millions of smaller dark matter subhalos. Each subhalo might host a dwarf galaxy, or it might remain dark, no galaxy forming within it. This creates a hierarchy. Large halos contain medium halos, which contain small halos, which contain smaller halos still. The counterintuitive finding. Here is the counterintuitive part. The abundance of dark matter. Subhalos predicted by simulations is much higher than the abundance of observed dwarf galaxies. Simulations predict millions of dark matter subhalos in a Milky Way-sized halo. But we observe only a few dozen to a few hundred dwarf galaxies. Where are all the predicted dwarf galaxies? This is called the missing satellites problem. If dark matter subhalos are abundant, and if galaxies form in dark matter halos, then dwarf galaxies should be abundant. But dwarf galaxies are rare. They are hard to find. The predicted number far exceeds the observed number. This suggests that either many dark matter subhalos do not host galaxies, star formation fails in most subhalos, subhalos are destroyed, tidal forces tear apart subhalos before they can form galaxies. Simulations are wrong. The predicted abundance of subhalos is incorrect. Dark matter is different. Perhaps dark matter is warm rather than cold, which would suppress small-scale structure. The correlation it reveals. The correlation between dark matter subhalo abundance and galaxy abundance reveals that star formation is inefficient in small systems. Most dark matter subhalos are too small to form galaxies. Gravity is not strong enough to hold onto gas. Star formation cannot proceed. Only subhalos above a certain mass threshold can retain gas and form galaxies. This creates a correlation. Dark matter halo mass predicts whether a galaxy can form. Galaxy clusters contain two components: ordinary matter, baryons, gas, stars, planets, and everything else made of normal atoms. Dark matter, the invisible scaffolding. The ratio of these two is called the baryon fraction. Here's the interesting finding. In the universe as a whole, baryons make up about 5% of the total matter. Dark matter makes up about 95%. But in galaxy clusters, the baryon fraction is higher than the cosmic average. Galaxy clusters contain about 10 to 15% baryons, the rest being dark matter. If baryons and dark matter were uniformly distributed, the baryon fraction should be the same everywhere, about 5%. But it is higher in clusters. This means clusters have preferentially captured baryons. Why does this correlation exist? The reason has to do with how galaxies and clusters form. Dark matter forms the gravitational scaffold. Dark matter accumulates in halos and eventually in clusters. Baryons, ordinary matter, are less abundant, but they are also affected by gravity. They accumulate in the same locations as dark matter. However, baryons have a special property. They can cool. When baryons fall into a dark matter halo, they can radiate away energy and cool down. This allows them to be compressed into denser configurations. Dark matter cannot cool. It remains at the temperature it had when it fell into the halo. So in galaxy clusters, baryons have preferentially cooled and concentrated. They are more densely packed than dark matter. This creates a correlation. The baryon fraction in clusters is higher than the cosmic average. Observational verification. The baryon fraction in clusters can be measured by measuring the mass of stars and gas in the cluster, ordinary matter, measuring the total cluster mass using gravitational lensing or the virial theorem, computing the ratio. Observations confirm that the baryon fraction in clusters is indeed higher than the cosmic average, typically 10 to 15%. Implications. The baryon enrichment in clusters has consequences. It means that regions of lower density space, far from clusters, are baryon depleted. These regions contain more dark matter relative to baryons. It also suggests that baryons are more concentrated toward massive structures than dark matter is. This creates an interesting inversion. While dark matter dominates in mass everywhere, baryons are preferentially in clusters. We mentioned earlier that environment affects galaxy properties. Now let's look at a specific correlation. Galaxy morphology, shape, depends on environment density. Specifically, in low-density environments, isolated regions, galaxy outskirts, spiral galaxies are common. In high-density environments, galaxy clusters, group centers, elliptical galaxies are common. This is the morphology-density relation. It is so consistent that if you know the local density of galaxies around a target galaxy, you can predict with reasonable accuracy whether it is spiral or elliptical. Galaxy morphology seems like an intrinsic property, something determined when the galaxy formed, not something affected by neighbors. Yet morphology is correlated with environment. Neighbors matter. This suggests that a galaxy's appearance can change over time due to environmental effects. Why does this correlation exist? Several mechanisms explain the morphology-density relation. 1. Mergers. In dense environments, galaxy collisions are common. Mergers tend to destroy disk structures and create elliptical morphologies. Isolated galaxies have fewer mergers, so disk structures can survive. 2. Ram pressure stripping. In clusters, hot gas strips away cold gas from galaxies. Without gas, star formation stops. The disk fades and becomes inconspicuous. The galaxy looks elliptical. 3. Tidal harassment. Frequent close encounters with neighbors heat up and distort galaxy disks. Over many encounters, disks are destroyed. 4. Dynamical heating encounters heat up the dynamical system. Gas heats up and cannot form stars. The galaxy evolves to a red, dead elliptical. Implications. The morphology-density relation reveals that galaxies are not fixed in their properties. They evolve in response to their environment. A spiral galaxy can become an elliptical galaxy if it falls into a cluster. A galaxy can transform from one type to another during its lifetime. This is a profound correlation. Location predicts appearance. Here is another important correlation. In the local universe, nearby galaxies, there's a relationship between stellar mass, the total mass of stars in a galaxy, star formation rate. How many new stars are being born per year? The relationship is roughly linear. Galaxies with more stars form new stars at higher rates. But here's the counterintuitive part. This relationship changes with cosmic time. In the early universe, billions of years ago, galaxies with a given stellar mass formed stars at much higher rates than galaxies of the same mass do today. This is called cosmic downsizing or star formation quenching. Why is this counterintuitive? You might expect that once a galaxy reaches a certain mass, its star formation rate would stay constant. The relationship should be the same at all times, but it is not. Galaxies are less efficient at forming stars now than they were in the past. Why does this correlation change over time? The reason is feedback from supermassive black holes and supernovae. Early in the universe, black holes and supernovae were less effective at quenching star formation. As time progressed, black holes grew larger and more powerful. Feedback became more efficient at heating and removing gas from galaxies. Eventually, a balance was reached where black hole feedback prevents further star formation. In the recent universe, this balance keeps most galaxies in a quenched state. Little or no new star formation occurs. The correlation it reveals. The evolution of the star formation rate-stellar mass relation reveals that feedback processes have become more important over cosmic time. Early universe, star formation is efficient, feedback is weak, galaxies form many stars. Recent universe, star formation is inefficient, feedback is strong, galaxy growth has slowed. This is a temporal correlation. Star formation efficiency now depends on when you ask. Zooming in from galaxies to globular clusters, dense balls of hundreds of thousands to millions of stars, we find another important correlation. The age and metallicity of stars in globular clusters are correlated. Metallicity is the abundance of elements heavier than helium. The early universe had very little metallicity, only hydrogen and helium. As stars formed and died, they created heavier elements, increasing metallicity over time. Globular clusters that formed early contain low metallicity stars. Globular clusters that formed recently contain higher metallicity stars. Why is this counterintuitive? This seems like it should be obvious. Of course, older clusters have lower metallicity because the universe had lower metallicity when they formed. But the relationship is more subtle. The precise age and metallicity of a globular cluster encodes its formation history. A globular cluster that is both old and has low metallicity formed very early, when the galaxy was young. A globular cluster that is somewhat less old but has higher metallicity formed later, after the galaxy had enriched its gas with metals. Observational significance. By measuring the ages and metallicities of globular clusters in different galaxies, astronomers can reconstruct the formation histories of those galaxies. Galaxies with many old metal-poor globular clusters formed most of their stars early. Galaxies with younger metal-rich globular clusters formed stars more gradually over time. The age-metallicity relation is a fossil record of star formation history. Here is a profound correlation that ties together everything from dwarf galaxies to giant ellipticals. The stellar mass of a galaxy is correlated with the dark matter halo mass that hosts it. But the correlation is not linear. Instead, there's a characteristic efficiency that depends on halo mass. The efficiency function. The correlation can be expressed as stellar mass equals efficiency, halo mass times halo mass, where the efficiency function has a specific shape. In small halos, dwarf galaxy mass, efficiency is low. Only a small fraction of the dark matter is converted to stars. In intermediate halos, Milky Way mass, efficiency is relatively high. In massive halos, giant galaxy clusters, efficiency is low again. Only a small fraction converts to stars. This is called the stellar mass-halo mass relation, or abundance matching. Why is this counterintuitive? You might expect that the efficiency should be constant, that the same fraction of dark matter is converted to stars everywhere. Instead, efficiency depends on halo mass. Small and large halos are inefficient at forming stars. Intermediate mass halos are most efficient. Why does efficiency vary with halo mass? Different feedback processes dominate at different mass scales. In small halos, supernovae are very energetic relative to the halo's gravity. Supernova feedback can blow gas out of small halos. Star formation is suppressed. Efficiency is low in intermediate halos, like the Milky Way. Gravity is strong enough to retain some supernova-driven outflows. Black hole feedback is starting to become important, but not dominant. Star formation can proceed relatively efficiently. Efficiency is relatively high in large halos, galaxy clusters. Supermassive black holes are very powerful. Black hole feedback heats the gas to very high temperatures. Gas cannot cool enough to form stars. Star formation is strongly suppressed. Efficiency is low. The correlation it reveals. The stellar mass-halo mass relation reveals a universal principle. The conversion of dark matter to stars is regulated by feedback processes. Feedback is the thermostat of the universe. It keeps star formation in check. This correlation unifies our understanding of galaxy formation across all mass scales. In recent years, astronomers have discovered a population of galaxies that defies the usual correlations. Ultra-diffuse galaxies, UDGs, are galaxies with stellar masses similar to dwarf galaxies, but sizes similar to large galaxies. They are spread out and diffuse. They have very low surface brightness, very faint per unit area. Why are they counterintuitive? According to standard models of galaxy formation, a galaxy's size should correlate with its mass. More massive galaxies should be larger. But ultra-diffuse galaxies are as large as the Milky Way, yet contain only a few billion stars, compared to the Milky Way's 100 to 400 billion. They violate the expected size-mass correlation. The mystery. How did ultra-diffuse galaxies become so large and diffuse? Possible explanations include they are failed galaxies. They started to form but were disrupted before completing assembly. They lost their dark matter. Through tidal interactions, they lost some of their dark matter halo, making them appear diffuse. They formed in a different way, perhaps through unusual merger scenarios or environmental effects. They are in the process of being destroyed. Tidal forces are pulling them apart. Recent observations suggest that many ultra-diffuse galaxies have unexpectedly high dark matter content. They are not dark matter deficient. They contain normal amounts of dark matter. They are just spread out over larger volumes. The correlation it reveals ultra-diffuse galaxies reveal that the size-mass correlation is not universal. Under certain circumstances, perhaps in cluster environments where tidal effects are strong, galaxies can become very large while remaining low mass. This is a reminder that correlations, while powerful, are not inviolable laws. The universe contains exceptions and anomalies that reveal new physics. Within individual galaxies, there is a spatial correlation. Metallicity varies with distance from the galactic center. Specifically, near the galactic center, metallicity is high, many heavy elements. In the galactic outskirts, metallicity is low, few heavy elements. This is called the metallicity gradient. Why is this counterintuitive? You might expect metallicity to be uniform throughout a galaxy if the galaxy has been well mixed over billions of years. Instead, metallicity varies systematically. The center is enriched compared to the outskirts. Why does this gradient exist? The metallicity gradient reflects the history of star formation across the galaxy. In the galactic center, star formation has been intense for billions of years. Many generations of stars have formed and died. Heavy elements have been produced and accumulated. Metallicity is high. In the galactic outskirts, star formation has been less intense or started later. Fewer generations of stars have completed their cycles. Less heavy element production has occurred. Metallicity is lower. The metallicity gradient is a fossil record of the galaxy's star formation history written across its spatial extent. Observational implications. By measuring the metallicity gradient in distant galaxies, astronomers can infer how those galaxies assembled. A steep metallicity gradient suggests star formation was concentrated in the center early on. A shallow gradient suggests more extended or ongoing star formation throughout the galaxy. The Tully-Fisher relation is tight, but it is not perfect. Individual galaxies scatter around the best fit line. This scatter, the intrinsic scatter in the Tully-Fisher relation, is itself revealing. What causes the scatter? The scatter in the Tully-Fisher relation is caused by variations in inclination. Galaxies are tilted at different angles. Edge-on galaxies appear different from face-on galaxies. Dust. Some galaxies have more dust, which obscures starlight and makes them appear fainter. Star formation history. Galaxies with recent starbursts are temporarily brighter environment. Environmental effects can alter galaxy properties. Intrinsic variations. Galaxies with the same mass can have different structure and composition. The correlation it reveals. The scatter itself is a correlation. The magnitude of scatter correlates with galaxy properties. Some galaxies scatter more from the Tully-Fisher relation than others. Understanding which galaxies deviate and why reveals physics not captured by the simple relation. This is a meta-correlation, a correlation about correlations. Within spiral galaxies, there is a correlation between bulge-to-disk ratio, the relative amounts of the central bulge versus the disk galaxy color. Whether the galaxy is blue, star-forming, or red, quiescent. Galaxies with large bulges tend to be redder, more quiescent, less star formation. Galaxies with small bulges tend to be bluer, more active, ongoing star formation. Why is this counterintuitive? The bulge and disk are different components of the galaxy. You might expect them to be independent, yet they are correlated with the galaxy's overall star formation activity. Why does this correlation exist? The reason involves black holes. Larger bulges host larger central black holes. This is the M-sigma relation again. Larger black holes produce stronger feedback, suppressing star formation. Galaxies with large bulges are therefore more likely to have their star formation quenched. Galaxies with small bulges have weaker feedback and maintain star formation. So the bulge-to-disk ratio is a proxy for black hole strength, which is a proxy for feedback strength, which determines star formation activity. The correlation reveals a causal chain, bulge size to black hole mass to feedback strength to star formation